insect who has a rotor. And I think it's really challenging task to imagine something like. Do you have an idea? Worms like rotors. Yeah, probably you're right. I mean, if they have some organ, something like rotor, if they have something that can rotate for unlimited number of rotations. So do you know? Do you have some idea? Yeah, right, right. We have at least one example of a rotating machine in nature, and it's good news. You know, I thought for sometimes that probably people created something that's more that that more unique than nature, but not. We have this example of bacteria, and it has a tail that rotates at really high speed, about 10,000 rounds per minute. So as I mentioned above, it's really important task, challenging task to hold this rotating part, to hold a rotor. There are four types of bearings, and we can divide them into groups with contact interaction and without contact and contactless. So the rolling bearings are the most popular now because they have very low friction coefficient. The sliding bearings are the thrust bearings in techniques, I believe. Both of them are contact, so they have some kind of wear. And the other group is contactless bearings. Electromagnetic bearings have very low friction. It is equal to zero, actually, but they are very energy consuming. It's really hard to hold a rotor with mass forces, and they have really complicated control systems. And the fourth type of bearing, we deal with this type of bearings, fluid film bearings. They have the effect of lifting something by means of very thin fluid film. So that's why I mentioned about that. We will talk a bit about hydrodynamics. So this kind of object is really complicated, and there are three main points should be achieved to make this fluid film bearing separate. First of all, this medium between rotor and the bearing should be viscous. Viscosity is a property of material to resist high-speed deformation. So you know that water can be deformed very easily if this deformation has low speed, but it's really hard to deform water with high speed. That's why it's really hard to run through the water. And some of the material has nonlinear properties of viscosity. In this case, they may behave like a solid material if the deformation speed is very high. So this is the first option, viscosity of media. The second option is velocity gradient. We need really high gradient between the turbocouples. So we have a huge gradient if the distance is small. That's what I tell, that the fluid film bearings has very thin layer of fluid. So the other option is stick condition. So it's a known fact from experience that fluids or gases has the same speed as the walls at the surface of this wall. So you may check it if you check your computer. You may see that they have dust on the surface. That's because of stick condition. And the third option is wedge effect. So the fluid flow domain should be convergence. So if we have, by the way, we have all these three options in this effect of lifting up car. And this effect is really dangerous. So in this case, we have all these 3 points, and in this case, car lose control. So in technique, this effect may be useful. It allows to hold a rotor with mass of several tons. And if we talk about what's going on in these fluids, so all we need is model the lifting force. And to find this lifting force and find out is it enough to hold the rotor, we need to solve this task from mechanics of continua. It's about I don't know, 30 or 90 equations, depends on formulation of this problem. And you realize that this problem is pretty complicated. Partial differential equations of motions, continuity equations, heat balance equations, and so on. So we have these two parts. First of all, we need to model fluid flow, and second thing, we need to model motion of the rotor. So, and when we study rotor dynamics, normally we can suppose that the fluid film can be linearized with Taylor set. For example, it is kind of a set of springs and dampers instead of fluid. This is the first way. The problem is that it works only near the position of equilibrium, and the other way, hard way, is to solve this nonlinear model all the time at every time step that we have. So then, if we solve this problem, then we can model a rotor with simple model of single mass or like a rigid body, or in general case, we should take into account flexible rotor. So that's the object in short terms. So we have this fluid flow, we have to model fluid flow, and we have rotor, we have to model this part too. So modeling of rotating machine with fluid film bearings is very important and challenging task. We need to, they always have vibrations, so it's unsteady process all the time, and we need to predict condition of rotor machines. So you heard about this this disaster or something with a rotating machine. It's an Shushenskaya gas, so it happens because of not really high quality diagnosis of this machine. And as I mentioned, the rotor has vibrations because of fluid film can generate vibrations, and rotor has imbalance. It also means that vibrations occur. And we have this very small gap. The thickness of this gap, this fluid film gap, is almost equal to the thickness of a paper sheet. So it's really important to have accurate enough model. We need to control that this K factor, that the amplitude of vibration should be less than the gap, right? It's obvious. Otherwise, we will have some disasters, some damage situations. So, and we can summarize this. What tool is preferable in modeling machines like that? And we suppose that MATLAB with Simulink is a really good option. It can be connected with SolidWorks or Autodesk. We can model some complex 3D rigid models of objects and then load them in Simulink. We also can write our own program, for example, for solving this hydrodynamic problem. MATLAB is not really good in solution partial differential equations, so we use our own programs. And we also may use some tools for application artificial neural networks, like NNSTART in the beginning, and then they also have deep learning model. And one more really important thing that is that we can connect our program with real hardware. For example, MATLAB and Simulink works good with National Instruments chassis, for example. So at what moment we realized that it's really good if we try to implement some kind of artificial neural networks and machine learning in solution of the task in this area. And then we checked a list of problems that we can solve using artificial neural networks. First of all, we can apply them for approximation of the lifting force. As I told you before, it's really challenging task. And we can use it for classification, for state recognition, for oh, I forget this title. Fault diagnosis. That's why we can diagnose the state of the shaft. We can also create some programs for predicting modeling and for control. And also we can check some levels of interaction between the artificial neural networks and machine, online, offline, and in other cases. So now talking about some specific tasks. The first task was the first one that we studied, and it's connected with supervised learning for prediction of the forces. So it's really, in terms of mathematics, this task for approximation is pretty easy. We need to find correlation between some experimental values, and we would like to find some function for this experimental values. So all we need to do is find an error, loss function, and minimize it using gradient descent and something like that. So it looks like finding minimal or maximal dip in some muddy water. We have some powerful gradient to implement this. In more general case, we can use something more interesting than linear approximation. We can use artificial neuron that has the same operation of linear approximation. Then we can add some non-linearity, some function like this. We can collect these neurons into a neural network, and in this case we have really powerful tool for approximation. So in solution of this task, approximation of reaction that is really non-linear, really complicated physical value, we applied very simple network with one hidden layer. This network receives in input position of the center of the shaft and velocity of the center of the shaft, and predicts the values of the lifting forces with two components projecting on the x1 and x2. So to train this model, we created a simulation model of this process. In this case, we solve these equations of mechanics of continua, and it takes a long time. So we calculated the trajectory of the rotor for some time, for several seconds. For example, in this case, we have kind of 1 million of training samples for the network like this. And we trained the network, and as the result, we got the network that predicts reaction of the fluid film very well. So we checked that it also worked with the case when the rotor have non-constant speed, run down of the rotor, for example, and it works very good. So you can see here that it was one of the problems in techniques, that if we need to calculate trajectory or behavior of the rotor accurate enough, we need to use this approach when we solve the equations of mechanics of continua. In this case, we need the real process happens much faster than calculation time. So it is a big problem, because if we need some program to predict what's going on next with the rotor, we need the algorithm that calculates faster than real time. So in this case, artificial neural network like this approximator works faster than real time, so we can use it for predictive modeling. Okay, and well, you see, it's really obvious the disadvantage of approach like this. We can calculate a number of training samples, and we can approximate only inside this trajectory. So we can make interpolation, but it doesn't work good in case of extrapolation. We just should take this into account. So, and the next task is fault diagnosis. This kind of tasks connected with logistic regression. In this case, we have binary response y and some independent variable x. So we need to find out the class. In this case, we have a bit more complicated loss function, and as a result, again, we have some algorithm, some program that receive some x and outputs diagnosis. So in this case, all we need is to find is to separate those several classes. And again, we can use some simple types of artificial neural networks. Well, maybe multi-layer perceptron for multi-class classification, or convolutional neural networks, and so on. So we solve this type of problem, fault diagnosis problem, using real data set. In this case, we apply it to our rotating machine. We add some multi-sensor measurement system on the basis of National Instruments chassis. We measure it pressure, so you can see this. This is the rotor machine. This is the bearing, very small gap between rotor and the bearing. We measure it pressure, contact resistance of the fluid flow. We measure it vibrations on the corpus of the engine and rotating machine. And it's really interesting fact that probably the best device here was the microphone that we situate near the rotating machine. It's not a simple microphone, it's professional Brüel Care microphone for vibro diagnostics. So we have all this data from sensors and recorded during the tests. And we made some problem with this rotating machine. We lost some bolts of one of the four. We also add some imbalance and some other problems. And we had 6 classes, including normal class, and try to diagnose of this rotating machine. So we've got a set of signals from the proximity probes. Oh, you can see them here, proximity probes of the shaft, microphone, as I said, accelerometers, and so on. Then we check the combinations of these signals and checks if we need all the signals or some specific signals. We use some kind of networks, one-dimensional, two-dimensional. And you see, we published a paper about this, and you see the table of the results, and it's really good idea to use something like autoencoders. It is a kind of filters of signal, and it works very well. And then even multi-layer perceptron works well. We also use some convolutional networks, and LSTM are good in processing of the sequences of signals. And this year, of course, we'll try transformers, as everybody do. So we also put emphasis on hardware. First of all, we try to implement it in small box in sizes like this, very small, with a Raspberry Pi, and it works well. And we also developed some industrial device, and we at the moment we collect some data from Quadro, from some plants, and we will try to analyze them in the near future. So that's about diagnosis tasks. So again, we need a lot of data, and if we talk about some industrial application, the main problem is labeling of this data, because we can't have access 24 hours to this plant, and it's really hard to find someone who adds some labels for this data. So we probably need some unsupervised learning methods, find some anomaly detection, so on. But the best way, of course, in fault diagnosis, if we need really high accuracy, we need labeled data. Okay, and the next step is control systems. And we tried again, we have this shaft, we have bearing, and we have, in this case, one more element control system. We try to apply some classic approaches, PID controllers, and we adaptive PID controllers and deep Q network, some the agent to check who's better. Some really briefly, some information about PID controller. Imagine that you have a pendulum somewhere in the outer space. You don't have gravity, you don't have friction, anything. And the task is to rotate this pendulum at a specific angle, phi0. So all you can do is generate this torque function, torque over here. So what's the torque function? We may have some trivial ideas. What if torque is equal to 0? Then nothing happens. What if torque is equal to 1, for example? In this case, the pendulum will have increase in speed, right? Then what if we combine this 1 and 0? Then it will keep this speed. So it's not super trivial task about finding this this function of torque, and it's the main idea is use something like this. So first of all, we can create this control signal in the following form. We can calculate the error between our current position, current phi, and target position, phi0, and the torque will be proportional with a negative sign, proportional to this arrow. In this case, we have something similar to spring, and in this case, the pendulum will have oscillation for infinity, right? But then we can add something else, the second term integral, or I like this term, derivative term, and this term is proportional to angular velocity. So we can model this PID controller in Simulink, and we can see that in this case, if you have these two elements, P and D, we can stabilize this this pendulum at position that we need. So that's the way PID controller works, and you can see some tasks that too hard for PID controller. Well, especially this one. It's really hard to create some algorithm of reaction of this dog for the interaction like this. So this task for reinforcement learning, of course, and some briefly intuition of reinforcement learning is that at each time step, a controller receives feedback from the system in the form of state signal from sensors and takes action in response. And the main problem is we don't know correct actions sometimes. And the main idea is to train agent after event. So we play the situation, we will got negative results most of all, then we analyze this and use it like a training samples. So again, we have these elements, environment and agent. We have information about the state from sensor. We have action, and we have reward for the action. So the task here is to maximize the reward in a task like this. And the most famous task, some kind of test task in this area is inverse pendulum. You may try to do it yourself. You may try to put a pen here and try to control it. Well, it's really hard, just 1 or 2 seconds, and that's it. So in this case, we may train the reinforcement learning agent, and the following task we have. We need to balance a pole on top of this movable cart, and we control the force on the cart. It may have positive value or negative value, and we can set reward +1 for each moment when the pole is on the top. So as the result, we can solve this problem very easily. It's available in help in MATLAB, for example, this kind of task. And we try to implement this control system to our object, to fluid film bearings. In this case, we try to control the pressure on the surface of the bearing. We use conical bearing, and in this case, if we control this pressure on the left side of the rotor, we can control geometry of this fluid film. In this case, we can control force, of course, because geometry, the gap, has a really great influence on the behavior of the fluid film bearing. So we created the model of this rotating machine. In this case, we made simulation tests. We created the model of this machine, and again, we need high-speed calculation. That's why we trained another network for approximation of the fluid film forces. As I told, this was task number 1. So we've got a really fast model of shaft bearing dynamics, and the task was connected with the limitation of vibration. So you see this blue line, and without control system, the trajectory intersect this blue line, and this situation is close to damage of the rotor. Then we train the decoy agent in MATLAB again, and we train this agent, and it able to control this bearing system. You see that the trajectories doesn't intersect this blue line. We also made some problems for the control system in the form of random external forces acting for the rotor, but it's okay, it's managed with it. And the next step, of course, we will try to implement this in real test rig, but the problem is that agents like this need a lot of examples. So we try to train it during 1 month, I guess. We created this machine, we start the pumps, and it operates for a month. It was not enough to train this reinforcement learning agent in real life. So it's really challenging to implement it in real life. I hope they will do it this year. Okay, and talking about this specific problem, actually we find out that PID controller can also solve this problem, because it's not so hard for control as this dock from Boston Dynamics. So we also try to find some more challenging problems in control systems, but anyway, it works. It may help to reduce friction. It may help to reduce oscillations of the rotating machine. So it's really nice stuff. Okay, we've been talking about this specific object, rotating machine. Now the final part, the third part of this lecture, I'm going to talk about physics-based learning. In this case, we study fluid dynamics in general, dynamics of viscous fluids again. So it's a very well-known fact that sometimes in physics we use some kind of laws. For example, Newton law, to solve a problem, to find position and velocity of the object. An alternative approach is we can use some conservation law, right? So we can, we know that the energy should have the minimal value. This is energy conservation law. We can use it. We also know some other tasks for this calculus of variations. For example, one of the tasks is to find out the function of trajectory that have minimal time for descent. So this problem is classical. It is solved. So it's not a linear. It is some kind of curvature, brachistochrone. And we also know this task from ancient times about the largest surface with limited perimeter. The answer is pretty simple. The largest surface is with the circle. And so all these tasks are the tasks for calculus of variations. In this case, we need to find some specific function, subintegral function, that that gives the functional, that is energy or time or surface, takes the minimal or maximal value. So if we're talking about hydrodynamics, we have this simple case, fluid flow between two parallel surfaces. We have analytical solution, and we can write an functional of energy, and this functional depends on velocity. So all we need now in solution of the problem using calculus of variations, we need to check all the admissible variants of velocity and find the one that gives the minimal value for this integral, for the energy, and that's it. And you know that we can make a trick. We can say that we searching for this velocity function among the power series, for example, like this linear, parabolic, cubic, and so on. And all we need is just to find these coefficients, these theta parameters. In this case, this variational problem that is very, very complicated, right? In terms of mathematics, we have a problem of function of multiple variables. This is functional analysis. It's a bit easier. And by the way, as you see, it is a typical task for artificial neural networks. So we can train the networks to minimize the energy and find the set of these parameters theta. Again, we can solve the equations, the set of equations that I mentioned in the beginning, and truly say we have some tools for solution any problem in hydrodynamics. We have ANSYS and something like that. They have some, we can find some limitation. ANSYS program is really expensive. It's hard to verify some results because we can get the results, but we don't know if this result correct. And again, this is the area for machine learning. Machine learning can help solve this problem with different levels of injection, let's say, injection of machine learning to the problem like this. Okay, and we have three types of physics-based machine learning. First of them is free of physics. Actually, it's a kind of supervised learning. For example, we have this problem of lifting force that acts on wing of the airplane. It's a really important problem too. In this case, we may use some network like UNet, for example. It has an image of the flow domain. That means we need a shape of this wing, an input, and receives the result in the form of pressure distribution, velocity distribution, and some other physical functions. So we can train this network using a lot of samples, and it works well. So at the end, network like this can predict velocity distribution, pressure distribution. We can calculate force and so on. Well, it's simple approximation, right? And then the next step is physical loss terms. When we have some physical equation in a form like this, and if you have a correct solution, if you find correct this function u, then left side part and right side part are equal. So in this case, we can add residual to the loss function in form like this and train the network. In this case, we can combine stochastic modeling and deterministic modeling, and it works well. By the way, I know at least one paper at this conference deals with physical loss for Schrödinger equation, I guess. Yeah, and the next level, this is what we done, is physics-based loss. We just find the loss function for artificial neural network that will be minimized And the result of this minimization is correct solution of this problem. We find the paper that deals with elastic problem, and they implement the network for approximation of displacement in the deformation domain. But the problem is we can't use approximations like this when we're talking about fluid dynamics, because fluids has vortices and something like that. It's we won't find any function, any power series, for example, for three-dimensional flow. It doesn't work for sure. So we try to find this physics-based loss, and the main challenge is that we can't just use any loss, any energy loss. We need to prove that this loss corresponds to this specific physical task. Well, I told above that we can we have this equation. We have to take into account non-Newtonian fluids, and we can compress these initial equations to Navier-Stokes equation and incompressibility equation, and we try to invent some kind of functional, and we need to prove that these two tasks are equal to each other, right? So we have some algorithm in this case how to do this. We can invent any function, any functional with this axis for coordinate. C is probably velocity or something else. So we can just write it, and then we should check the Euler equation for this functional. And if this Euler equation is matched with initial Perrier partial differential equation, in this case with Navier-Stokes equation, for example, then we found exact solution. Then we found exact loss, I mean. Otherwise, we need to try one more time. So the theory of this Euler equation have one limitation, that all these functions, psi, all these unknown functions, so should be fixed at the boundary. So we generalize this equation in case if we have a second derivative, if we have three-dimensional space and so on. So it's not really hard using tensor calculus. And then we take Lagrange variential principle as the basic one. So here it has one term connected with energy of internal energy of fluid, and one term for external energy. And the main unknown function here is velocity. In our case, we modify this functional a bit, and we use this psi function as unknown. It is a kind of flow function in hydrodynamics, and its derivative, its vorticity is equal for velocity. So just you use one more derivative, and that's all, with the same meaning. And we proved that this functional works for non-Newtonian fluids. It don't need this term for outer forces and so on. And I tried to implement this using artificial neural network. So algorithm in this case is pretty easy. We can use the network like this, multi-layer perceptron, or in this case, the network receives coordinates of the flow domain and outputs the unknown function. It has some predictions, and then using these math equations, we can calculate velocity and other mechanical parameters, and we can calculate the functional. That should be minimized. So in this case, we don't need a data set. All we need is domain. I don't think that this algorithm really good, because we need to modify it for every flow domain that we have. But the next algorithm, I like it more, because in this case, all we need is this picture, this mask of the flow domain. And at the beginning, we generate this unknown function, psi, add the mask on this unknown function, and use UNet, for example, that generate again this image. So when we have image of this psi function, again we can calculate derivatives, calculate velocity, and so on, and we can calculate our loss. And again, we made several iterations. So in this case, we check flow domain like this. We need 10,000, 20,000 iterations to calculate the fluid flow. And you know, believe me, this algorithm is really really easy to implement. So we test the model, the first model and the second model, and it works well in general. And the goal of this this algorithm is that when we need to model some fluid flow, all we need is a picture of this flow domain. For example, you can see here nail fold of a human. You see this is the test rig. So I think that you can't see this on the screen, but I can see the motion of the cells in a capillary of a nail fall. Well, it's a really challenging problem for us, and we try to use this algorithm to calculate velocity field, velocity distribution in a capillary, and it works well too. So we just use this image and calculate the fluid flow. So it has some limitations, of course. All this variation calculus, I mean, in mechanics, deals with stationary problems. So unstationary flows, it's really hard to calculate. We can calculate some quasi-stationary, and that's it. I think that in general it's very good stuff, and it's really easy to implement, and it's free of charge in comparison with ANSYS. And the challenging task for us, next task, is we're going to use MRI images of vessels of a human body and try to calculate some tasks of blood flow, drug delivery, and something like that. Okay, I don't have much time. I'm gonna talk a bit about my experience. So I have classical education in basics. I studied mechanics, and one day I realized that I'm interested in stochastic modeling. So in general, we have two approaches to modeling, right? We have white box. When we know the laws, we can model the process that we study, and it looks pretty cool, especially if the task is not really complex, right? The other approach in this case, so we can write this law of motion of this object and solve it easily. Find the velocity at any time, find the position of this object at any time. This is the deterministic modeling. Otherwise, we can create a set of experiments for measuring velocity or position of this object. Then we can use some tools for approximation, some simple or neural networks, for example. In this case, we deal with black box, with stochastic modeling. And I was wonder which approach is better. And when I was a student, I suppose that this white box is the best way, because we know the laws. We can't solve any problem without this stochastic guessing, yes, something like that. But then I realized, this is about my own experience, why I realized that I can't solve problem like this using all this deterministic modeling, because this is the fluid flow in a cup of tea, right? And the challenging problem here is to set boundary condition on the surface of the spoon. It depends on motion of this arm, of the shoulder. It depends on condition of this person. And I realized that it works something like Heisenberg uncertainty. So in terms of physics, if we try to implement super correct problem in terms of physics, we have this problem that we can have, we can't exclude really high errors in terms of mathematical modeling. So in this simple idea, this simple problem turns me to the stochastic modeling and to this conference at the end. Okay, this is about our work for the recent years. I would like to thank my colleagues and my teachers, Lagrange, Euler, and so on, for the help with these tasks. And that will be it. I would like to say that we also will have a conference, online conference in Innopolis in this December. So please take part in this. If you have some questions, you can write me in Telegram and email. Thank you very much for your attention.
Thank you, Alexey. This has been a very interesting talk. Do we have any questions from the audience?
How many times you need to apply your calculations in real plants?
You mean what task are you talking about? In fault diagnosis, something like that?
Yeah.
Well, in real plants, we keep on studying this problem. So I don't know. We just collecting data from the real plants. But it's really good that they asked this question. We have received advertisement from RAO VS or something like that. It's really big organizations in energy, and they will have hackathon in Innopolis. They will give their own data from their plants, and the prize is, I forgot, about $500,000 for the first 3 places. Again, if you write me, I will send you a link. I have an idea to add it here, but I didn't have time. So we will have next month some real data from RAO. Yeah, and the more the better. Simple answer for this question.
Thank you.
Any other questions? Then I guess I have a question as well. It's been a very interesting talk about physics-informed neural networks. In our lab, we actually also use them in a biomechanical context. And I was wondering, how well does this approach in your case generalize to different size of this image? Because in our case, when we try different images of the same size, so basically a channel with different bumps, then it works really well. It interpolates between all these things. But when we try to change the size of this domain, it actually performs much worse.
Yeah, I get it. It has influence on, in my opinion, it has influence on numerical differentiation. So we are finding numerical derivatives to find velocity. In this case, we compare intensity of pixels. So if we have higher resolution, we have more accurate derivative. So yes, if we use high resolution image, we have better results. But also we can fix this problem with types of approximations. We can use parabolic approximations, third order, fifth order approximation, and so on. It also may help with this problem. But yes, it has influence.
Okay, thank you.
Okay, thank you very much. See you next time.
Okay. Our second invited speaker for today is Professor Peter Slot from Amsterdam University, and he is going to tell us about complex networks and dynamics in those networks. Peter, are you with us?
I am.
Yes, it's
Hello?
good to see you. Hello. So, Peter, the floor is yours.
Okay, excellent. You can hear me. That's good. So let me share my slides with you. I hope you can see this.
Not yet.
So today I'd like to share with you some ideas about a relatively new research area, which is the field of complexity science, which is very much related to computational science. And so what I like to do is to basically take you through the motivation for this part of the research and some recent results. So if you have a question or you want to interrupt me, feel free to do that. So let me set the scene first with the motivation why this research is relevant and what has motivated people to develop this new science of complexity science. So here is an overview of some of the big problems we all are facing, all the way from climate change to global health issues, through to geopolitical problems that we're all facing, and to the big divide that we see between the poor and the rich. And of course, all these things are somehow interconnected. And it feels that we are in a world where we are changing the world much faster than we can actually reason about it. And so what we need to do is to come up such a system in a way that if we do an intervention, that things don't get worse. And believe me, that's one of the biggest problems. Just identifying how complex a problem is and what the cause and effects are is one, but then figuring out what the consequences of your interventions are is much harder. And so what we need to do, we need to be able to predict what is the consequence of our actions. And like Niels Bohr was saying, prediction is hard, particularly when it's about the future. And of course, it was a little joke of his, but it's a fair point. And here are some examples of how bad we are in predicting things. So the president of the Michigan Savings Bank, who was an advisor to Henry Ford, at some point said, the horse is here to stay. There's no way that the automobile is ever going to be a serious thing. It's a novelty, it's a fad. I think history has proven him dramatically wrong. And then, of course, there's a story about Titanic, where the president of the White Star Line, or vice president, said there is no danger that the Titanic will sink. The boat is unsinkable and nothing but inconvenience will be suffered. I like that one. Nothing but inconvenience will be suffered by the passengers. And then there was Steve Ballmer, the CEO of Microsoft, said there's no chance that the iPhone is going to get any significant market share. No chance at all. And we know that that's pretty different. Now, the Prime Minister of the Netherlands, in an interview just 10 years ago, said, those 80 Leopard tanks that we have, we don't need them anymore. We will not have a ground war in Europe anymore. So history tells different. And of course, there was Trump. No one was actually thinking that Trump would win the election, but in the end he did. Anyways, the bottom line is we are very bad at predicting things. And that's because everything is very much, interwoven with other things, and we need to unravel what's going on there. And the point is that if you do not really understand what's going on, if you don't see those connections and the consequences of those connections, it's very hard to design a policy that works. Let me give you a few examples that kind of exemplify this. One of the research that we've done is looking into segregations in a school. And what we actually found is that if you close the schools which are most segregated, so segregated, as you know, means that you have a school only for whites, a school only for blacks, you have a school maybe only for Islamic and maybe for the Christians or for the Orthodox, whatever. So you have these segregations going on, and we showed that if you close the schools that are mostly segregated, so that it's very like monolithic schools, that actually the total segregation in the schooling system gets bigger. So it's a very counterintuitive thing there. Later on, I will show you that if you take out the kingpins of cannabis production, so that's let's say criminal networks, then you can make those production even more efficient. So again, you do an intervention in the system, and the outcome is completely different to what you expected. Same goes for research that we did also together with ITMO, actually, university, about the consequence of better HIV medication that might even lead to more HIV. Anyway, so there's a lot of examples there where we do interventions in the system with a certain goal, and that we actually obtain the opposite of that goal. So why is that? Why is it so difficult? Well, the first thing is that we trust too much on data by itself rather than having a deeper understanding of what's underneath the data. Particularly nowadays where AI and machine learning are making this massive progress, we tend to forget that the data comes from something, that it comes from something underneath it, that there are processes, mechanisms underneath it. And if we stop at the moment we see the data, so to say, and process the data without really going into the origin of the data, we might run into troubles. Here are some examples. So, for instance, the data that came to us about the Brexit and about the elections in the US, everybody thought, it's not going to happen. No Trump. There's not going to be a Brexit because, looking at the data, it was like that. But it turned out differently. Same goes for looking at just purely looking at the data of earthquakes, looking at the way Google gives us information about the progress of the flu through Google Flu Trends. All these things were not indicative of what actually happened, and so there is something special there. And here's an example where we actually show that how easily you misinterpret what's going on. So here's a beautiful example of the Babylonian clay form, it's called, where the Babylonians in this cuneiform they present their calculations of the displacement of Jupiter, and it was amazing. They were really very accurate. They could accurately predict at what point in time where Jupiter would be. And so the Babylonians did that by extensively looking at the skies, making notes, and basically gathering data. They were very, very successful at predicting where Jupiter would be. And a couple hundred years before that, so 500 years for BC, the Mayan astronomers were able to understand the cycle of Venus up to a few hours. And that's, given the time we're talking about, is amazing. It's an amazing feat that they were able to do that. Yet, the Babylonians thought that the Earth was drifting in some kind of primordial ocean, and there were just holes in some kind of dome around it, which were the heavens and the stars, if you like. And the Mayans thought that the whole universe was held by a couple of beasts that kept the universe in its place. So even though they could do things with the data, they had no clue what actually was underneath it. And that's okay for systems that are very regular, and there's not much you can interact with that system. Then it's still okay. It's okay you don't understand what's going on. But if the system is something you can interact with, then you do want to know what you're talking about. So I would like to say that this idea of a lot of scientists nowadays, particularly data scientists, that if we uncover the pattern in the data, then we understand. Well, I just gave you these two examples of the Babylonians and the Mayan culture. It's not true. It's absolutely not true. It's not that we understand once we see the pattern in the data. We might, get an idea of some kind of dynamics that's going on, but that doesn't mean that we understand what's underneath it. So that's the goal that we. I'll just skip this for a moment. So that's the goal. Is that so? What we need to kind of look at is that, maybe my way of looking at it is saying that, data is dead without what-if models. And so a way to look at it is to say that data is a record. It's not a conclusion, it's not an insight, it's not even a solution. And data analytical predictions only work well if the future is fundamentally the same as the past. But this is the thing we really have to get into our mind for the rest of the talk, that that's true, right? If I have a good analysis of the past and if nothing is changing, then of course it's a predictor for the future. But for any serious system that we want to study, it either evolves into some kind of other dynamics, so it will change in the future. We interact with it, and then also it will change in the future. So we need these what-if kind of models to support and understand that. And then we need to kind of look into the historical data, what will tell us that that's basically the realm where machine learning work. We need to look at real-time data, and we need to look at future data, which comes from the process of modeling, and where of course computational science comes in. Now the reason why the future is not the past, so to say, is because of all these underlying causal interconnects that evolve the system into different states, and that's the field. Understanding those causal interconnects, if you like, is it's typically the field of complex systems. So, what is this complex systems? Well, we call them also complex adaptive systems. Well, I think I like. My favorite definition is that, of course, when it's complex, it's not simple, which is like, a no-brainer. But that means basically that we cannot reduce it to the elements out of which it constitutes. The moment we reduce it to the elements of maybe we have this reductionist approach to the complex system, we lose what we're looking for. So here's an example of a bird flock. These are starlings, beautiful patterns. They create these microscopic waves, if you like. They come about from individual birds, but the moment you look at the individual bird, you actually lose the thing that you might be looking for, which is how come these beautiful microscopic patterns, how they emerge from that. And that's I think a quite beautiful example of a microscopic process driven by microscopic processes. But the moment you drill down, you actually lose what you're looking for. And the other little movie you see here is on the immune system, where we have exactly the same thing. The moment we drill down into the small molecular processes, we will lose a larger understanding of the microscopic behavior of the system. Okay, so complex systems are everywhere. Some characteristics is there is no mastermind. There's not one particular one saying, this is the control. There is not, in the case of these ants, there's not one ant that says you have to do this or you have to do that. Or in the case of the birds, it's not particular bird doing this, giving directions or whatever. There's self-organization, which is the ants that form the bridge, or the caterpillars here, where the joint movement of the caterpillars is much faster than one caterpillar ever can have. It's a remarkable thing that it kind of evolved over time. Complex systems are also adaptive. They adapt to the environment, and this is important. They adapt to the environment that they themselves create. It's like the birds, they create this microscopic environment, and then they act on that microscopic environment, but they've created it themselves. So you get this kind of massive, complex feedback loops. And we see those complex systems everywhere, pandemics, living organisms, the immune system I mentioned, but also in cities and in markets and in economy and, in things like the Internet of Things. So they're everywhere. But how do we study these things? Do we have computational tools to play with that and to have a deeper understanding of how all these things are intertwined? So one of the, I would say, important characteristics of complex systems is what we call emergence. And emergence basically means that at a certain level, that could be a temporal level or a spatial level or a functional level of the system that we are studying, some new characteristics emerge that have not been there before. Let me give you an example. So if we would say that our thoughts arise from the firing neurons in our brain, which is I think a reasonable assumption. And okay, we have this 80 billion neurons, and each neuron is connected with about 10,000 other neurons. So you get this massive explosion of connectivity, and that results in our thoughts, in our actions, in our movements and everything. And so you can ask yourself the question: how much of the thoughts that are generated by all those neurons firing at different times in different places, how much of the thoughts that are generated in our brains are present in one neuron? And that's the moment you start to think about it, that's a weird, a bit stupid question, right? So a thought in one neuron. But then ask you, okay, how much in 2, how much in 3, how much in 1,000, how much in 100,000, how much in a billion, if you like. And there, at what point, if I scale up that thing, at what point do I have that thought? Can I identify, if you like, that there is a thought emerging? And I already used the word emerging here. And that's a fundamental question. We don't know. We just don't know. We don't know where that phase transition, whatever you want to call it, is happening. But we do know that thought is not present as such in the lower lying, in one neuron. But it's really this combination of things that results in the thought. And so Murray Gell-Mann, I would say the discoverer of the quarks, formulated it when I met with him a couple of years ago. He said, how wet is one molecule of water? It's the same kind of question. We all feel intuitively that it's a stupid question. How wet is one molecule? Well, of course, in one molecule, you cannot talk about wetness when you talk about one molecule of water. But at what point in time, how many molecules do I need in order to start talking about what we mean with wet? And again, that's wetness, if you like, is an emerging property of these molecules of water. And so we want to understand how these interactions between the subsystems are happening, and can we find telltales of this emerging property of the dynamics of the total system by looking at the elements, and or can we reproduce that through computational methods? So all this thinking about complexity science kind of motivated Stephen Hawking in an interview in 2000 to say, I believe that the 21st century will be the century of complexity. And And what he meant with that is that we need to start thinking about, more about the systems at large and how things are interacting with each other in order to understand the world around us in a better way. Which means that we have to go look for, cause and effects and interrelations of systems. So again, a complex system is elements interacting with each other and quite often in a nonlinear way, creating an environment to which they react themselves, evolving over time and resulting in emerging properties. So one example I would say is the emergence of cities, and that's. I mean, it is remarkable when you start to think about it, that cities actually exist. And why do they exist? And why are they efficient? How are they efficient? And something remarkable happened in around the year 2005, for the first time in the history of humankind, for the first time there were more people living in cities than outside of cities. So within our lifetime, we have experienced that, I would say, that massive change where there are more people living in cities than outside of cities. It is like it's like I would say that in retrospect, this will be considered one of the most important things that happened to humanity. We've been, as Homo sapiens, we've been around for, about 200,000 years. And just like 10 or 20 years ago, we went through that phase transition to have more people living in cities than outside of cities. So what is a city and why is it so popular? And can we quantify that popularity? And there's lots of research already in the 1960s by Jane Jacobs and others that said, basically cities present situations with several dozen quantities or all varying simultaneously in a complex connected ways. So intuitively, she could kind of phrase that. And people were making, in those years and the 20 years after that, they were making observations that, for instance, when a city doubles the size, then the economic productivity per capita increases 15%, which is amazing. So what does this mean? This means that if I take you out of, if I take you out of Amsterdam and I put you in St. Petersburg, which is roughly twice the size, then your individual activity, resulting in maybe the amount of papers that you produce, the amount of patents that you create, or even the amount of software that you write, increases by 15%, which is an insane thing, but it's quite true. These are facts. But at the same time, there's a negative thing with it. Also, if you double size the city, then the amount of crime per capita increases. So this is normalized as per capita. So it's not. So if you have, like, say, 100 crime happening in city A, and the double of city A will of course produce 200 crime, but it will produce 216. So it's really this additional surmount. And so this spawned off a lot of research, and particularly driven by a good friend of mine, Geoffrey West, and one of his disciples, Louis Bettencourt. Disciples, I should say. Louis Bettencourt, beautiful work where they tried to kind of uncover all those different properties of cities. In terms of the size of the cities, and so they found these scaling factors here, and make a note that we're really talking about this this kind of scale-free power law behavior of the properties of the city, and so you see that for patents it is a 27% increase, for the GDP is 15% increase, serious crimes increases, new AIDS cases increases, but it's an interesting thing. And at the same time, it becomes more efficient in the sense that to service the same amount of people and the same amount of cars, so to say, then you need less gas stations, you need less road surface. So there is an intrinsic efficiency in those cities. And we now now we see that effect everywhere. We see it in crime, in pollution, in noise, in segregation, etc. So these are the things that we see happening. So what we try to do ourselves is to see, can we link that? This is actually ongoing research. Can we link that to mental disease? So can we, or mental disorders at large? So that would be like, depression, anxiety, illicit drug use. Can we really pin that down? And it's proven to be pretty hard, as you can see from this messy slide. But we do see an increase. So on the bottom, on the horizontal axis, we see the let's say the urbanicity, so the amount of the size of the city, if you like, and the effect we see on the vertical axis. And you do see some kind of incline, but it's not very, very strong. But you do see some kind of incline, particularly in depression. So there seems to be an association with depression and city size, which is again interesting. And all these things, we believe, they come about from networks, from individual networks, from social networks, from infrastructural networks like car networks, road, public transport networks. That's the bottom line. The understanding now is that somehow those networks create some kind of efficiency that allows for this super scaling of larger cities. But not only for that, as I will show you. This is a famous graph. Maybe you have seen this at some point in time. This is what you're looking at is a high school dating graph where students were asked with whom they were dating over a past period. And the blue ones are the boys and the red ones are the girls. And there's lots of interesting things here in this graph. But first of all, just the realization that we're looking at the graph is interesting. But of course, you see, very active individuals around here. This is like a hub, if you want to call it. A boy with a lot of girls dating, but there's also girls with a lot of boys dating. Here's an example. But you see a lot of other things here. You see that if we can influence each other in terms of changing our opinion, you can actually see that opinions can move through the whole system. I don't know if you can actually see my pointer, but the opinions can actually move in circles through the whole system. And you can also see, there are certain spots, like over here, where, if you would take out that individual, the whole system will unfold. So you see all kind of interesting aspects of this topology. And of course, we can, do nice calculation this because we can reformulate a graph like this in a matrix and just enumerate all those individuals from 1 to, what was it? I think it was 280 or so, on horizontal and vertical, and then just put ones and zeros. So ones are connected and zeros when they're not connected. You get a nice matrix, and you can do some nice linear algebra studies. Figuring out what actually this topology means. So looking at those networks, people have been doing that quite extensively. We find those networks, and particularly this particular type of networks, which we call scale-free networks, we find them everywhere. Recently, we published some work on production networks in chemical plants in different countries. Particularly also in the Netherlands, looking at the functional structure of production networks. But we find them in companies, we find them in the same scale-free networks, the power laws, if you like. We find them in protein networks, in metabolic networks. We found actually, this is a study we did also partly together with IDMO, where we studied protein networks of HIV. But also in opinion networks, we find these characteristics. And the interesting thing is that what you would expect is if you look at the connectivity, if you look at, let's say, this boy that has like 7 girls connected to him, you say, okay, that's a hub, and that's an exception. So, if the K is the connector here on the horizontal axis, then you can see that, okay, you would expect that There are a few that will have a lot of connections, and a few that will have a few connections, and in between there's some kind of average behavior, if you like. But actually, the characteristic of these networks is different. We see these power characteristics saying that the probability of having k connections is k to the power some kind of gamma minus some kind of gamma. And that's important. That's a massively important thing, because it basically means that we're looking at some kind of fractal structure where the scale is lost. And it also means, this is very important, that because it's a scale-free distribution, like I show you later on, because it's a scale-free distribution, and it's a parallel, because of that, there is no average. Or another way to say it, the variance can go to infinity. And that's a very important consequence for all these complex systems that we are studying, that I get to back in a moment. So here's what we see. So we would expect that the left part of the panel, we expected this famous bell curve. Most nodes have some kind of links, and you have a few that don't have, and a few that have a lot. But what we actually see is this power law. Very many nodes with only a few links, and a few nodes with a very large number of links. And that's a remarkable thing that is underneath almost every complex system that we talk about. And this has a consequence because of this power law. This doesn't have an average, like I was saying, and might have an infinite variance. And then the question is, if I get data from this kind of processes, and I will do my machine learning tools, but then hang on, machine learning means I try to learn something, but how can you learn something that has no average? How can you learn against something that has an infinite variance? If average walks away, how can you design a program that starts to learn? Because the next iteration, the average will be different, because there's basically no average. So that's an important consequence. So it means that we throw more data at it. That means we throw basically more exceptions in, and that means that our learning algorithms will not converge. And so that the deeper reason for that is that in complex systems, quite often it doesn't make sense to talk about cause and effect because there's so much intertwined that it's difficult to unravel that. And I think the next slide will say something about that.
The markets.
I hope you can hear this.
All these firms with all these very complicated and complex technology systems and how they interact makes the entire system of exchanges, high frequency, brokers, and the interaction between.
Oh, you missed something. I'm sorry. Let me do that again.
The markets and the interplay in the industry between all these firms with all these very complicated and complex technology systems and how they interact makes the entire system of exchanges, high frequency, brokers, and the interaction between the technology. It makes it a complex system. And so, for example, the flash crash is a perfect example. There is no cause and effect that you can point to. What caused the flash crash is a nonsense question. It makes no sense in the context of a complex system. And if you were to replay the same sequence of events identically, there's no guarantee that it would cause a flash crash again. That's the nature of complex systems.
Is it the correct remark that a lot of insiders don't understand the markets?
I don't think anyone understands what's going on. I think that's another quality of complex systems, that they're kind of beyond human comprehension. The markets and
So that's an interesting statement, right? He says it's kind of beyond human comprehension. So we can actually stop our talk now here because, what are we trying to do then? But this is a fair point. This was about the flash crash, and the reason why the flash crash happened is because algorithms were trading at the speed of light. One algorithm discovered there was something happening with a certain stock and reacted to that, and other algorithms started to react to that algorithm, etc., etc. And that was a cascade of processes are completely running out of control and making that stock market collapse. And so, yeah, but even though these cause and effect are very much intertwined, we need to still, see if we can make some kind of sense out of it and study it. And that's the field of complexity science. And so here are some examples of things that we are doing. And I won't tell you, of course, I don't have time to go into the details there. I will show you some other things later on. But these are some examples where we can actually apply these notions of networks and these notions of intertwined causality to study what's going on. And one is social economic inequalities in health, where we look at the amazing thing that we see in larger cities, a massive increase in diabetes, which we know, of course, is associated with genetic defects, but also with things like social economic status. So understanding, how much of the diabetes pandemics, if you like, is driven by genetic disorders or physiological disorders, and how much is driven by social economic aspects. Connecting these two things is of course by definition massively complex, because you try to connect basically genetic and molecular processes with processes that are happening on the social level, like how much do these people earn, what's the size of their family, where do they live, and all those aspects, and trying to connect those together and understanding what's happening, but not only understanding but also being able to do interventions in it in a way that it actually gets better and not has these kind of side effects and unexpected and unwanted side effects. Is a hard thing, and we're doing quite some work on that. I already talked a little bit about resilience of industrial clusters. This is a thing nowadays, particularly very hot because of the energy crisis, and so in the energy crisis, the government is looking for, can we take companies out of use less or even stop using gas? But then you have to think about how those companies are connected to other companies in terms of their half products, in terms of sharing resources like people and materials. And then you see by taking one company off the grid, so to say, it can have massive log-on effects in the rest of the cluster of the industry. So understanding that again requires a deep study of that kind of interconnectivity. And I already mentioned the other two, and I'll say more about it in a minute. So two kind of foundational discoveries I want to share with you in this field, and that I think were quite surprising, and it took us quite some time to understand what's going on there. But I think I want to share this with you because I feel that it gives you a deeper understanding of what we're talking about here. So here we have a network, and we ask ourselves the question, we want to send signals through this network, so to say, and we want to understand, signals could be like, you could observe signals like, how opinion changes. It could be signals in gene regulatory networks, where one gene is upregulating or downregulating another gene, or this could be, how messages go through your friends' networks, etc. And so we basically look at the dynamics, if you like, on the network, and we want to have a better understanding of that. And what we found, quite counterintuitive, what we all expected is, so here again on this left panel you see the green, so that's again the amount of connections. Think of this board with 7 connections. So the higher K, the more connections you have. So you have the real hubs here on the right, and the language, if you like, on the left. And what we found is that the way information is dissipating through that network is not driven by the extreme, so to say. It's not driven by me being somewhere in the peripheral or someone is very highly connected, but it's driven somewhere in between. I'd like to call these the Goldilocks. Somehow they seem to fit perfectly. So it's the intermediate connectivity that actually drives the dynamics in these networks. Now, this was a theoretical study where we basically used ideas from physics, particularly the concepts of Ising spins. And of course, you could say this is a theoretical result. So how true is this? And of course, we validated that. Well, here first, I'll show you a bit more. I hope you can see this, what I'm talking about. So this is a peripheral node that changes its opinion, that changes its state, up, down, regulating, whatever, from red to green. Having relatively to none consequence on the rest of the network. And here now I'm changing one which has intermediate connections. And then if I flip it from green to red or the other way around, it will percolate through the whole network. It will actually be propagated, if you like, through the whole network in a very efficient, dramatic way almost. And here you have a highly connected individual or a node. And that's basically stabilized by the network around it, so it actually has less effect on what's happening further on in the network. So we validated that. We looked at different studies, and so we see the same effect in networks of neurons on Petri dishes. We see it in the social network of word of mouth marketing, and we find the same thing in gene regulatory networks. So it seems to be a universal characteristic that it's in the dynamics of the network, particularly the short-time dynamics of the network. The driver nodes are not the hubs, they're not the peripheral nodes, but it's the ones that are actually in between. So I think that's an interesting discovery. Another discovery we made, which has an interesting consequence, is the following. I'll just go here. When you want to send information from one side of the network to the other side of the network, so here from left to right or from right to left, green to green if you like. And if I would then superimpose some noise on this network, noise being that I connect or disconnect randomly some nodes or change some links, then the efficiency with which that information goes through the network actually goes up a little bit. And then, if I add more noise, so I remove more nodes or I change more links, at some point that will collapse again. So here's an interesting observation. I want to send information from one side to the network to the other guide. That takes an amount of effort, energy, whatever, hubs, like hops. And then I introduce some noise to that system, and then actually it gets better. It's got to do with basically the way the system can evade local lock-ins. And it's like, an energy landscape, but it can, basically jump over barriers in a more efficient way. This is a phenomenon that we know from physics, which is called stochastic resonance, which is pretty cool. And we actually see that stochastic resonance effect. Of course, when you take more nodes out or you change more links, at some point the whole thing basically will collapse and you will not be able to send information across anymore. Now the point is, and this is interesting, and I hope you guys are still with me, I'm almost done by the way, that if you think of this, this means that this might be the reason why nature wants to organize itself in these powerless scale-free networks, because they are robust. They can get a hit and still survive. So a protein or a gene regulatory network can still produce proteins, even though some of the connections might, for some time be disconnected or changed. And that's exactly what you want, of course. Otherwise, we all would fall apart. So this might be one of the reasons why nature kind of invented, if you like, this kind of topology for its interconnectivity. So the last example I want to give, and then I'm almost done, is just noticing what a network does or describing the complexity in terms of networks is one way, but then you also want to think about what is the consequence doing an intervention in these things, in these systems. So together with the Dutch police, we started to look into criminal networks, and particularly cannabis production networks. And so these are, these are things where there's an illicit group of people coming together, having some space where they start to grow cannabis, which is of course hidden from the outside world. And they need a mastermind, they need someone who owns that place, they need an electrician, they need people to work on these plants, and they need, of course, people to produce and sell, etc. So it's a whole, what we call in sociology, we call this a value chain, but it's also a network. And in the Netherlands, there was an effort to stop these cannabis productions. And what they found is that, the way they do that is they take out the kingpins, so the ones who are mostly connected in those networks that are, mostly in contact with other people, so the hubs. But what they discovered actually is that, almost every week they dismantled about 30 to 40 cannabis productions every week, again and again and again, even though they kept on dismantling. So it looked like things were not really progressing, were not getting much better. So we started looking to that by building up the networks. And so we actually had 3 networks. We had a network which was a result of the arrest data. So because they were dismantling 35, every week, these people were arrested, their associations were written down, with whom they were working together and what they were doing and how they were part in that whole network. And that's created, from this arrest data, created the criminal network that we could study. But we also had soft data of police walking in the streets, noticing that this guy was part of that network and is talking to another guy, went down to his desk, wrote that down, and we got that information also. And then the third amount of information is, of course, that criminals are also in social media. So you can also look to whom they are connected or to whom they are talking, etc. So that also gives you some kind of information. And you can then combine all that information and relate that also not only to whom they are connected, but also what their function is in the network, in this value chain. So there's a guy who owns the shop, and here the size of the balls, if you like, is an indicator of the amount of connections. The guy taking care of plants, there's a guy building the plantation, doing anyway. So you get all those functions and how they are connected, and then you can ask yourself, okay, what would happen if I disrupt this? By, for instance, when I have that whole network, I take out the in-between nodes, or I take out the hubs, or whatever. And you can play these games now in your computer, and looking at the feedback loops, the consequences of these interventions. I'll stop this guy 1 moment. So what we see here is what we found in the left upper panel. What we found, if you remove the nodes, if you remove the hubs, and you calculate the consequence of the efficiency of the network, that actually the network gets better. So the production of cannabis increases by removing the hubs of the node, which is actually what we saw, what the police saw in real life. So taking out the hubs, that we can show in this study, taking out the hubs, it makes the network stronger. The reason for it is you force the people to rewire their hubs, to rewire their networks after taking out the hubs, but they rewire it in a new environment because immediately, the time has changed, so there's not other, embedding networks are also changing over time. So they can optimize their network and actually get better. This is a remarkable thing. Of course, because it's a complex system, it's always more complex than you think. By the time we published this, and as this guy was trying to talk about, and let me go back to that. So this guy was here. No, he doesn't want to talk anymore. This guy here.
Wetenschapper Peter Sloot probeert een heel andere werkelijkheid in.
This was on the news. and it basically ended up in a kind of documentary describing this whole process. And even though once the police started to use this knowledge that we were able to obtain from this study, and we saw that there was a decrease in cannabis production. After this was on the news, of course, the drugs, the criminals in the crime networks also saw the news and also understood what was going on and changed their behavior. So you see, because it's always feedback loops in feedback loops in feedback loops, and interventions in a system could make things worse because now you're intervening and the cannabis production goes down, then you share it to the rest of the world. The criminals see it, they change their behavior, and it becomes even more harder to reduce the networks. So this is a fun example, I think, where it really touches upon the heart of complex systems, but it also gives us lots of fun to study these things. So I think I want to end with the last two slides here. Is one by Heinz Pagels, who said that the great unexplored frontier is complexity. I'm convinced that nations and people that master the new science of complexity will become the economic, cultural, and political superpowers of the next century. And I tend to agree with him. I think having a deeper understanding of complexity, all the way from the man in the street to the politicians, will really make a difference. And I was lucky enough to spend 10 years in Singapore, where the Singapore government is really embracing complexity science in the way they look at the big problems that they are facing, like their dependency on water and energy from places outside of Singapore. And they really take into account all these feedback loops and try to use the tools that we have in complexity science to make sense of that. So the last slide, the takeaway lessons from this talk that I was giving you is one: be careful with data. Data is basically dead without what-if models. We need the what-if models to do that. Complex systems, what are they? They are non-linear interacting elements. They evolve over time. They create these emerging properties, and we can study them partly to networks. Not all complex systems can be captured in networks, but most can. We have these Goldilocks that drive the network dynamics. It's not a peripheral node, it's not a highly connected node, but it's somewhere in between. I gave you examples of cities and crime, and the typical tools. These are all computational tools that we have to study complex systems. Are things like group model building, causal loop diagrams, system dynamics, obviously, complex networks, and agent-based models. And there's more. There's a lot of mathematical tools coming from physics, renormalization tools, etc. But that's more, I would say, on the theoretical level. But on the computational experimental level, we have a lot of absolutely cool stuff to study these interesting processes. And so I guess that's it I wanted to talk to you about today. So if you have any questions, feel free to ask me. Thank you.
Thank you. Thank you, Peter, for your beautiful talk. And do you have any questions from the audience?
Thank you, Professor Sloot, for the interesting presentation. I have several questions, if you don't mind. First of all, you demonstrated that noise may increase quality of the model, and you also demonstrated the plot with maximum. Would you please explain in more detail how to add noise? Is it input noise, output noise, or noise inside with some mechanism like dropout or something like that? And what is the nature of this maximum? Can you explain it? This is the first question.
Yeah, excellent question. So what I mean with noise is a very good question. What I mean with noise is, assume you have a network that does something. Let's say we have a protein network or a gene regulatory network that produces proteins. So it does something, right? And it does that because it needs to transfer information between the network, upregulates or downregulates other genes. So there's signals going through the network. Now, assuming you have such a network, and assume that that network is a complex network, meaning a scale-free power-law network, then if you would just calculate the amount of, let's calculate the effort that it takes to get a signal from one side to another side of the network, and that could be calculated in terms of the amount of steps that you need in order to get there. Then if you then would say, okay, I take out a node, I take out a gene, or I just rewire somewhere in that network, I rewire the connection between some nodes. Then if you do that, that's what we call noise, these two types, well, actually another type. Then actually what you will see is that the amount of steps that you need in order to get to the target node, on average, again, this is all average, of course, on average again, it will get less. So you are more efficient. And the reason for it being considered, if you think of it like a dynamical system, where you have to walk, where you have like energy barriers that you need to pass. And going across the energy barrier takes you, costs some energy. And if you introduce some stochasticity, you actually randomly, every now and then, make a jump and allows you to jump over this energy barrier. And so as a consequence, you can reach places in that fitness landscape that you could not have reached before. Like I said, this phenomenon is called stochastic resonance. And so it gets a little bit better, but you also understand if you throw in too much noise, if you take out too much links, or you change the algorithm of moving through the network too extreme, then at some point you will not reach it anymore at all. So there has to be an optimum. It's getting better, and then after it has to get worse. So there's always an optimum. Where that optimum exactly is, that's a very good question. We don't know. It very much depends on the system itself, of course, but you cannot say that in advance. So I guess I answered your question.
Yes, thank you very much. And one more question, if you don't mind. I've been thinking for several months if artificial intelligence may replace government, for example. What do you think about such a complex systems? Is it possible in near future? What do you think about it?
That is, this is a wonderful question. I wish we could have another hour to talk about this. A few thoughts. First of all, we see AI already at different places taking over decision processes. And I'm personally very much against that. And I can talk about that forever, but for instance, you see AI algorithms taking over decisions in health, in health support, and in medical doctors. For some, it's pretty good, and AI is perfectly capable of detecting tumors in an image. It's absolutely brilliant, and it can assist rather than decide on its own people to make a decision. But when we talk about really complex systems, so where there's all kinds of dynamics going on, like a government, like in a country, it is a country, of course. You are absolutely right. The country, of course, is also one big complex system. Like I told you, I will never be able to make reasonable decisions there because it's always building. It doesn't have what-if models underneath it. If it's just using data that comes to it and try to make a prediction of coming out of that. If it's combined with what-if models, then I think it will be more reliable. But still, so it then could still it could help people to decide on very complicated and complex questions. But it should always be an assistant. I think we always should have a person in the loop, and that's the same. Like we need some. We don't want to change an autocracy with another autocracy. We don't want to change the dictator with another dictator. You know, if you have a dictator ruling a country, you don't want to have another dictator being an AI system ruling that country. So we still want to have this kind of democracy, even if in that democracy is an AI. That's okay. The AI system could also contribute to the discussion in the democracy, figuring out, you know, do we really understand what's the consequence of what we're doing? So, as my short version to the answer to you would be, we have to be extremely careful in giving power to AIs. But we, of course, there will be a future where there will be more power to AIs, and we have to make sure that we guarantee that we are always part of that decision process, and that we don't leave the decisions just to the machine.
Okay, thank you very much.
Right. Do you have any other questions, maybe? I think I have time for one short question. I don't see anyone. So, thank you again for joining us today. And I hope we can meet in person at the next conference.
Hello, my name is Atom Brudikin and I head of Lab of Virtual Reality and Training Systems, a part of the Institute of Hydrodynamics and Control Processes in St. Petersburg State Marine Technical University. Our lab team has completed a study which is to be presented today as a paper called Diagnostics of Motion Sickness, Kinetosis, and Training Resistance of Hello, my name is Atom Brudikin and I head of Lab of Virtual Reality and Training Systems, a part of the Institute Control Processes in St. Our lab team has completed a study which is to be presented today as a paper called Diagnostics of Motion Sickness, Kinetosis, and Training Resistance to it in VR maritime simulators. Motion sickness. View from point of view. Approximately from 5 to 15% of adults suffer from motion sickness, also known as kinetosis in one way or another. Motion sickness occurs due to more or less prolonged and changing accelerations, the symptoms of which are usually nausea, vomiting, cold sweat, headache, drowsiness, yawning, dizziness, loss of appetite, and increased salivation. There is a kind of motion sickness which occurs as a result of immersion to the VR environment, VR-derived motion sickness. Motion sickness is usually identified during sailing in the sea, not during the professional training, which makes an early diagnostics of being prone to motion sickness of great importance for maritime specialists. Currently, VR is already being used in study of motion sickness. Our study is partially funded by the Ministry of Science and Higher Education of the Russian Federation as part of World-Class Research Center program, Advanced Digital Technologies. Goals of our study to investigate the direct effect of a visual channel on the symptoms of motion sickness, including changes of channel parameters. Also, we want to assess the possibility of training a control group of users with vivid symptoms to reduce the symptoms of motion sickness. We investigate the motion sickness and methods of reducing manifestation and symptoms by dynamically changing the viewing angles, as well as assessing the influence of peripheral and stereoscopic vision, including their various variations. In our experiment was 50 participants. All users are adult males and females between the ages of 18 and 45. You can see on the diagram. In a total, all participants successfully completed all tasks of the study. We used an experiment Oculus Quest VR headset. Specs you can see on the screen. Test area for experiment was 3 on 5 meters. On the software base, we used the digital virtual multi-user environment. Is a versatile and scalable SAS and PAS product that includes both software and hardware modules for quick and easy development of VR-based simulator solutions. This product is already used for training personnel and additional education, maritime simulators, ground operations simulators, etc. So the key benefits of used software is client and server implementations. Most hardware is compatible with any environment. Individual or group usage via internet or your local network. Multiple tasks can be solved using the environment, including tasks raised by Industry 4.0. Great scalability and versatility. Out of the box, the environment is great, is really ready right after installation. Software and hardware modules can be added and or extended. So the preparation of experiment. On picture A, you can see not cropped view. On picture B, you see the cropped view of user. So this is one of the points of our research. The first part of study in case of identifying the symptoms was a close one. Consisted of a few 10-minute sessions during which the complexity and the load were increased for the user. At this stage, the user intolerance to the VR equipment and the basic parameters, 0 stage, were revealed. During the second part of the study, close to the user was relocated to the speedboat with the maximum roll and pitch on the waves. At this stage, the maximum angle of view and the roll and pitch impact on the user were investigated. The third part of the study, close 3, included the user moving around on the speedboat along a given trajectory with a maximum roll and pitch on the waves, sharp turns, and the requirement to turn the head in the horizontal plane. Up to 40 users may experience discomfort of a varying intensity in VR. To eliminate the discomfort, the IPD was adjusted for each user in experiment. This significantly reduces the dizziness for users who are prone to motion sickness while maintaining the maximum realistic training in VR. Users have completed the training part of the study, namely training with the same parameters, but with a decrease in the viewing angles and their gradual increase. All tests in the training were similar to those performed to detect the symptoms, but the significant difference was in the decrease of the viewing angle. In the case of extreme exposures, the user did not use the binocular vision to minimize exposure to video content. Test series during the study. First, similar to clause 3, but without binocular and peripheral vision, and without roll or pitch. Second, similar to clause 3, but without binocular vision and a gradual increase in roll, pitch, and viewing angles. Third, users undergo the test again with a maximal load of similar to clause 3. Thus, data is obtained on the state change for users with a gradual increase in the load of the percentage of users who can get rid of or reduce the symptoms of motion sickness when using the revealed technique. 5-minute session with a 5-minute break were set as time parameters for test to conduct. First, initial step of the study was to identify the basic symptoms of motion sickness, such as dizziness and nausea, directly in VR, using clause 1. So on a diagram, you can see total number of users. You can see that there are 6 users with identified symptoms when the pitching is changed, 2 users with identified symptoms when pitching and head position are changed, and 1 user with identified deviations when moving. In the second stage, clause 3 was applied. Users with identified symptomology when moving ahead, with a change in the roller pitch and also in the head position. From 50 users, 9 of them with identified dizziness when moving, and 2 of them with identified deviations when moving. Also we testing users with identifying symptomology when a speedboat is moving and turning. From 50 users, 11 of them with identified deviations when moving, and 4 of them users who need external support from laboratory assistant. After conducting the studies, symptoms of motion sickness were revealed in 25 cases out of 100, which are made possible to define a control group to study the possibility of reducing symptoms of motion sickness during training with increased load. Total number of users was 50, and 25 of them identified vestibular deviation. 11 of them find mild symptoms when peripheral vision is disabled, and 4 of them find mild symptoms when using the monocular vision. The identifying symptoms when parameters are dynamically changed with a maximal impact on the user's test was used to train with the following changes in all primary tests with cropped images: monocular vision, peripheral image shutdown, reduction of the roll and pitch to their minimums. Sessions were held for 5 minutes with 5-minute break, and after which the test with the maximal load were repeated. After the testing, we found in the first session 8 people with a slight deviation in the vestibular apparatus. In the second session, that number was 15. In the third session, we found also 15 users with slight deviation, but also we found 4 users with severe deviations in the vestibular apparatus. A control group of 25 users demonstrated that the motion sickness symptoms were identified only for 15 users. Majority of symptomology was reduced, but for 7 users it did not change at all. Overall summary, it was revealed that the changes in the vector and the speed of the object to which the user attached has a great influence Users were able to control the change of direction and speed during experiment, and the most of users prone to motion sickness independently reduces speed both steering angles, tuning and traveling speeds. We have confirmed that the reduced viewing angles as well as monocular vision or lack of peripheral vision can significantly reduce symptoms of motion sickness. This is due to a decrease in the effect of visual sensors on the user. So in our future steps will be used to conduct more related experiments in VR. We consider involving more maritime specialists and train motion sickness resistance for each user. We plan to obtain the more data, which is a clone and realistic to physiological data and as possible when motion sickness is observed. This simulation environment can provide full immersion and allow us to get more perspective simulation approaches for maritime industry. Thank you for your attention. Have a nice day.
Dear colleagues, I believe that we have one of the co-authors online, so we may ask some questions. If you don't mind, I'll start. Okay, the title of this paper is Diagnosis of Motion Sickness. Would you please demonstrate us some estimation, some accuracy of this diagnosis system? And that's the first question, right?
To interrupt you, actually, the title of the paper says diagnostics of motion sickness, not the diagnosis. So actually, we only tried to we maintained some diagnostics to identify it. It was not about making a diagnosis on that.
Okay, one more question. Do you have some response from doctors about your work? And please.
No, unfortunately, we haven't demonstrated our results to the doctors yet, but we have one military doctor which is going to be involved in our future testing, which is based on this paper. So this, I believe that this should be mentioned in the presentation, but we decided that we're going to present it at fullest in our future papers.
And one more question. Would you please tell us about your plans of the further research? And one advice, probably you should add some video in your presentation. It will make the topic of this research more clear, I believe.
Yes, okay. And as for the future plans, as in this study, we used the existing data on motion sickness, and that was enough from the medical point of view. And for the future plans, first of all, we're going to involve a military doctor to assess the results that we have. And also, we are going to use more hardware to get more realistic physiological motion sickness, and that hardware is going to be the platform of GeoSphere type. So that's it, I believe. And also we're going to involve more maritime specialists because now most of the participants in the study were actually students, and only those of who were older, they were maritime specialists. But actually, the study was intended to improve their resistance to motion of sickness. So yes, that's the plans.
Okay, thank you very much. Probably someone else have some questions offline or online. The authors need feedback. So please, any questions? No, not now. Okay, good luck with your work. And the next presentation in my plan is by Ariel Scagliotti. He is online, I hope. Let's check.
Yes, he's online.
Yes, hello, can you hear me?
Yes, we can hear you. Please start.
Uh, I'm with a really bad connection. Is it possible to pass the video and then I am connected for any question, please? Is it possible?
Ariel, unfortunately, we don't have your video. Maybe we try to listen to you online. No, just a second. Just okay, Ariel, we can prepare your video in several minutes. So in this case, the next presentation is by Ksenia Shkileva, and she also have video.
Hello, dear listeners. My name is Ksenia Shkilova, and the subject of our work is explainable artificial intelligence techniques in medical signal processing. The purpose of this work is to build methods of explainable artificial intelligence for the task of classifying medical signals. The objectives we have set in the process are indicated on this slide. The relevance of the work is that since deep learning algorithms are the kind of black box for the user, it is very important to display computational results in a human readable area to show how which input parameters contributed most to the final decision. In this work, we consider the class of methods called attribution methods. The purpose of this class of methods is to assign a share of responsibility for a particular result to each aspect of their respective input. On the example of the image, we see the pixels. It is red areas that influence the final forecast to a great extent. That class is crocodile. And the first and the simplest method is gradient input. The idea of this method is to use information about the gradient of the function, for example, some model, which tells us for each input measurement whether the function will increase if we take a tiny step in the direction. If the output of our function is the probability that the image contains a crocodile, like in previous example, then the gradient basically tells us how much each dimension increases the prediction of crocodile model. Consider a deep neural network that receives input X and output S. There C is the total number of output neurons here. Although some specific target C small is given, the purpose of the attribution method is to determine the contribution R of each input attribute X to the input S. Then the final attribution is equal to the product of the partial derivative of the output with respect to the input and the input itself, like here. The next method is integrated gradients. So let's say we have some basic input or baseline X, which can be an absolutely black image or an image with a mean value or zero vector. We consider the straight path from the X baseline to the X input and calculate the gradients at all points in the path. In particular, integrated gradients are defined as the integral of the gradients along the straight path from the baseline X to the input value. The integrated gradients along the if dimension for the input x and the baseline x is defined as follow on the screen formula. The next method is LRP. This method uses network weights and neural activations created by a direct path to propagate the output back through the network to the input layer. The value of the contribution of the intermediate neuron is called relevant values. Consider the value of R, called the relevance of the unit I for layer L. The algorithm begins with the output layer L and assigns relevance to the target neuron with the output of the neuron itself. And the relevance of all other neurons are 0. It is equation 1. The algorithm works layer by layer, redistributing the prediction score S until the input layer is reached. One of the recursive rules for the redistribution of layer relevance to the next layer is the rule described in equation 2, where we defined that Ji as the weighted activation of neuron I on neuron J in the next layer. And Bj is the additive, is a BS. A small number is added to the denominator to the equation of the equation to avoid numerical instability. And once the input layer is reached, the final attributes are defined as here. The next method is deep lift, is similar to the previous one. The target neuron is assigned an attribute that represents the relative effect of the activation of the given unit at the input of the source network X as compared to the activation at some reference input X or baseline. So the baseline is often selected to be 0, and relevance propagation is described in equation 4, and the attributes of the on the input layer are defined as here, like in the previous method. So in this paper, we consider the task of analyzing medical signal data and predicting diagnosis. The distribution of data is shown in the diagram. For classification, we use two neural network architectures. It's UNet and ResNet, and the results of the classification are presented in the table on the right. So let's take a look at the example of interpreting all the results for the ResNet. This ECG belongs to the STTC class, so it's STT segment chains. The features of this diagnosis are peak-shaped T waves or inverted T waves or ST segment elevation. So the darker the color, the more an area contributes to the final prediction. And in this case, all four methods more strongly highlight the regions corresponding to the peak-shaped T wave, which is a sign of this disease. So the gradient input, deep lift, and LRP methods make this much clearer. The same example for the UNet network. The areas of interest are already less highlighted, but it can still be seen that the areas with T waves are the most important. So this is more evident in the deep lift method. In some previous paper, we also considered the task of interpreting the same ECG data, but used the SHAP method. This example refers to class CD, or cardiac conduction disorder. This diagnosis is characterized by a wide, often M-shaped R wave in the leads V5, V6, and 1. The figure on the left, SHAP method, shows the orange areas that contribute more to the forecast. They just match the M-shaped R waves. The same areas highlight are attribution methods on the right. The only difference is that the calculation of Shapley values takes longer than the calculation of attribution. And as a conclusion, for the results of the interpretation, it turns out to be quite difficult to identify any one of the best method of attributes. And as for the neural network architectures, the interpretation for ResNet gives more indicative results than for UNet. And in addition, comparing the methods with the SHAP method, the first ones show the best result in terms of performance. And that's all. Thank you.
Dear colleagues, it seems that we don't have co-authors online or offline. Am I right? So in this case, we can't answer the questions. Anyway, we wish luck with the research for the authors of this paper. And the next paper is by Ariel Scagliotti. He haven't presented his work in his own session, so we will listen to him here. The same situation with Gisara Kulatunga, and we suppose that this kind of interdisciplinary section is probably a good idea to connect control problem, medicine problem, and so on. So, okay, Ariel, we're gonna watch your video first, and then I hope we'll have some questions.
Assemble an expert knowledge model using predictors and hyperparameters taken from literature and compared it with a final model called FNet assembled with the methodology we are presenting here. The expert knowledge model was assembled using the hyperparameters shown in this table, the normalization with a mapping between -1 and +1, the hidden neuron function is a tangent hyperbolic sigmoid. The output neuron function is a linear. Weights and bias initialization according to the function Gaussian-Withrow. The learning rule is a Leverman Marquardt, and the data division is random. The last 4 parameters correspond to the early stopping technique, which allowed us to stop the training and achieve a good conversion. The predictors are also taken from literature. The particular matter of 10 microns share the same trends that the target. The sulfur dioxide, NOx, and hydrocarbons are precursors of the target. The relative humidity has an impact on the growth of particles. The wind has an effect on the transport and the dispersion of pollutants. And the boundary layer height contains the particles in the troposphere. The architecture of this model is a classical feed-forward and back-propagation neural network. Using different hidden neurons, we found that with 14, the neural network achieved the best results. So, about the new proposal, we start reducing the dimensionality of the input space of the model. In the left side of the slide, we can see a matrix correlation between all possible predictors. The dark blue and dark red squares correspond to high correlation between them. And when this happens between two variables, this means that they are providing similar information, redundant information to the model. So, when we find this between two variables, we discarded the one with the less correlation with the target. In the right side of this slide, we can see the final map of a self-organizing map neural network, which is a classification technique. And every plot here shows the effect of every variable in the final map. And in this way, we can find patterns that showed us similar information given by same variable, different variables. So when this happens again, we discard the variable with the less correlation with the target. So in this way, we reduce the dimensionality of the input space, taking into account the correlation, the linear and non-linear correlation between variables. The single testing model, SNET, is a model that we use to test individually every variable that we didn't discard in the former step. So in this way, it's a neural network, classical neural network, with just one input variable, just one input neuron. We used different indicators to see how good is every variable to predict the target. So we organized them from the best predictor to the worst one, and we used them in a testing bench model called TBNet. For this model, we filtered the target so we can smooth the signal, and then we used a gradual feeding technique, which means that we start feeding the model with the best predictor, then with the second one best, and then with the third best, and so on, till the model doesn't show any improvement in the indicators of performance. When we have the best predictors, then we test all the possible hyperparameters and architecture for the model. And in that way, we achieve the FNet model. The FNet model was trained with these hyperparameters shown in this table. The red ones are the ones that are different from the expert knowledge model, a normalization with zero mean and standard deviation of 1, hidden neural network function, a Rydell basis, and a learning rule, a gradient descendant. The rest of the parameters are the same from the expert knowledge model, because in this case, they had little influence on the sensitivity for training. The predictors are the ones that we taken from the former steps, are slightly different from the expert knowledge model. The architecture also is a feed forward and back propagation, but we added a recurrence of 1 hour delay. This means that we feed the model with its own output. We tested this model with a different number of hidden neurons, and with 20 we found the best results. So here we show the main results. The expert knowledge model and the FNet model with our methodology both has a good serialization and conversions, but the FNet model showed better indicators of performance. As conclusions of this, we can say that the expert knowledge models are suitable to have a glance about the situation of a phenomenon, of a modeling case, but this can be always improved. The FNet model assemble showed good results among the best on literature, and it also allowed us to deal with low data availability and quality, which is the case from Buenos Aires Air Quality, for example. For the next steps in this work, for our future work, we want to optimize this model. This means that we want to find better quality of data to train the model and a longer time period, and then adapt it for prognosis. This means to predict particular matter concentration 24 hours ahead. So this is it. Thank you very much. To know more about this, we let you hear a QR code to access to more details to our work. Thank you.
Thank you, Ariel. Dear colleagues, do you have any questions? Maybe we have some questions online. Okay, so far you're thinking about your questions. I have one. Ariel, would you please explain in more detail the technique of reduction of dimensionality? Have you checked this technique with one versus all, or you tried some combinations of the factors? And have you tried to solve this problem without reduction of the dimensionality? Would you please explain a bit more in detail?
Yes, thank you. Yes, I tried without reducing the dimensionality, and the main problem that the network showed was an overfitting. It means that it didn't predict well with new data. So reducing the dimensionality allows is like a more flexible neural network for prediction in that way.
Okay, thank you very much. Do you have any other questions? No, then Ariel, good luck with your research. Hope to see you here next time. See you.
Thank you very much.
Okay, and the next presentation is by Ksenia Sakhatova. And after the next is by Mustafa Lawal. I think that we have both presentation online and we have co-authors online. So, Ksenia?
Can you hear me?
Yes, we can.
Okay. So good day. I would like to present the results of my research, which was dedicated to the explainable methods for object detection in computer tomography. Let me start. Okay. During our work, we collected a bunch of articles which describe quite precise requirements of clinicians to AI-based systems. Further, for experimental part, we have chosen a data set and a model along with methods of interpretation. And consequently, based on the derived results, we built an analysis of the tested methods. So let's look at them. Oh, no. There are two key questions we highlighted on the slide from aggregated articles with interviews with clinicians. And according to the first question, the main drawback that decreased trust of practitioners is the black box nature of AI-based systems. For example, we know input data, we obtain the results of the model's prediction, but there is not any explanation how it gets it. And there are also technical and ethical concerns about the data accessibility and availability, along with its structure and distribution. For example, how the data should be anonymized to keep patients' confidentiality, or is the model biased to the majority class? Thus, clinicians do expect the following information from such systems to have a better understanding behind decision-making process. It's listed under the second question, and it's estimation of the importance of the contributed features, provided degree of uncertainty of the model, simplified representation, and revealed temporal changes of the features. Medical domain is quite challenging on its own, and this puts some limitations on interpretable methods as well. In the table, you can see restrictions of some explainable concepts, let's say. In our work, we mostly have focused on feature visualization and the generation of attribution maps. And indeed, some of the methods provided hardly understandable results in human interpretable terms. What about test data? We had computed tomography scans annotated with resist diameters. Thus, we had CT scans of different body parts with labeled lesions. The network we used is called MULAN, which stands for Multitask Universal Lesion Analysis Network. Input data flow through the DenseNet backbone, which extracts features for further fusion in a corresponding layer, and then these aggregated and enhancing features are propagated to detection, tagging, and segmentation branches correspondingly. Tags here contain description of the body part, its type of lesion, and various characteristics of the detected lesion mined from the radiological records of deep lesion dataset. On the slide, you can see simplified classification tree of the interpretable algorithms, where lists represent those methods that we have chosen in our research. There is no strict taxonomy, and single methods may contain characteristics of a couple of categories. So let's talk about the methods and their results. The first one is agent class activation map. This is an algorithm that generates visual explanation of principal components derived from the learned representation of the convolutional layers. The method does not utilize propagation of gradients, which makes it less prone to classification errors. But in our case, generated explanations are quite ambiguous, as you can see. For example, both second and fourth images highlight dark parts of the image as more important in prediction, even if it cannot contain any lesion. The next bunch of methods includes gradient sharp, layer gradient sharp, and layer activation methods. Gradient-based methods supposed to be applied for differentiable models and considered as model-oriented. Thus, the first part of experiments used the features extracted from the backbone. Due to the DenseNet specificity, sum of all attributes calculated with gradient sharp provides redundant information about contribution of all features. However, looking into the specific layer, it gives more precise information, which could be seen in the second column, which is layer gradient sharp. Layer activation sharp layer activation, method tells us about activation of hidden units rather than about contributed pixels. In this first part of experiment, the contribution maps do not really reflect the whole magic of object detection that takes place after the feature being extracted. Looking into the network that generates proposals to be bounded with boxes, we see that layer gradient shaft performs much better, highlighting those features that contributed to the prediction. Comparative analysis of the attributions derived from the whole model and the specific layer helps in better understanding of reasoning behind the output of the model. Perturbation-based methods showed poorer example results, and occlusion attribution maps captured dark parts of the images as important to the final prediction. Thus, technique of occlusion is crucial for medical images, and in our case, grayed out patches that are already in grayscale were assigned as less important than more contrast parts of the image, let's say background. Unlike occlusion, Lime methods discard the whole segment, which affects the generated attribution map. However, despite perturbation technique, model could be highly sensitive to so-called adversarial attacks, and even small changes may modify prediction, increasing importance of the small patch. It makes these methods less appropriate in medical settings. Comparison of the tested methods has been done in terms of consistency and infidelity. All methods could be considered consistent except only Lime. Due to the color-based segmentation method, Lime quite sensitive to small changes that are not very visible for human and professional eyes. Also, produced large superpixels remain approximately the same, with the light attribution map differs drastically, as we can see in the last two rows. They differ drastically from slice to slice for both linear regression and decision tree. Another, this was more subjective metric, but another objective metric that can be quantified is infidelity that we measured. It evaluates the degree to which the explanation algorithm is able to capture changes in predictor's inference caused by the significant perturbation. And in our experiment, gradient shaft obtained the lowest infidelity with regard to small noise distortion, unlike the last two, Lime and Adrian. So, in conclusion, I would say that if we deal with the object detector, it's better to derive features for your interpretation explanation from region proposal network, if it is there in the architecture of the detector. Gradient-based methods are much more preferable, and for medical images, whereas perturbation-based methods should be accurately revised and domain adapted before application. And in our experiment, in our research, gradient shaft provided the most optimal result in terms of consistency and infidelity metrics. Thank you for your attention. I would be glad to answer your questions.
Thank you, Ksenia. Dear colleagues, do you have any questions?
Thank you for your talk. I have a couple of questions for you. So first, maybe I just missed that. How much data and what kind of data was used to train your networks that you studied?
Actually, the whole size, the total size of the data set is about 20 gigabytes, and we have used pre-trained networks and analyzed explanations and interpretations only in terms of test data set, which is like several gigabytes.
And in terms of the number of images, how many is that roughly?
Sorry.
So in terms of the number of images that you have, how many is that? Is it, I guess, many thousands? And they also come from different
I
Dockers?
guess it's more because it's hard to say because we had like a lot of catalogs, directories, which represent the specific study case of the patient. It means so one catalog has a bunch of images that represent this study case, and we had like a lot of this catalog, this directory.
Okay, I see. Thank you. And another question is, some of the methods show this dark areas in the images as actually important, apparently. So is this just an artifact of these methods, or could it be that this network uses these dark areas to determine what kind of organ it is, for example, or the shape of it, something like this, and bases its prediction and part on that?
Maybe I will go back to that method. You mean this methods, right?
Yes.
Sorry, your question is about why the network, why we get these explanations where black backgrounds have been interpreted as the more important, right?
Yeah, I'm asking if this could actually reflect something about that network and not just a problem with the method.
Actually, my assumption is that it's mostly for the method because I have tried to occlude, let's say, patches with grayscale baseline, and it do not give really good results as well. And reasoning about these results also, I have reviewed, let's say, that methods, this occlusion method uses grayscale patch to kind of to calculate importance of the ablated pixel.
Okay, thank you.
Pixel it considers as more important than if we ablate gray scale pixels with the same almost color. So if you get the idea.
Okay, I see. Thanks. I have no more questions.
Vikas, do you have any other questions? Maybe online? No. Then Ksenia, thank you very much. I probably have some questions. I think that I can write you a letter about my research. I need some consultation. Okay, thank you very much.
Thank you.
And the next presentation is by, oh, give me a minute, Mustafa Lawal Abdurrahman. We have online presentation. Mustafa, please share your screen. And after the Mustafa, we have offline presentation by Israel Homan. Okay.
Hello? Okay.
Yes, we can hear you.
Okay. I'm Mustafa Abdurrahman Lawal from Department of Mathematical Science, Abubakar Tafawa Balewa University, Bauchi. Here in Nigeria, I'm presenting our paper titled Deeper Architecture for Brain Edge Prediction based on MRI images using transfer learning technique. The main outcome measure in brain edge prediction is the difference between an individual predicted age and their chronicle age. It's referred to as the brain age gap. The prediction of human aging is an intriguing problem with numerous applications. It may be based on different factors, including the appearance of face, DNA, radiographs of the knees, chest plate, and other areas. The majority of studies on age prediction have relied heavily on the age. Investigation were to apply image processing and machine learning approaches to solve this problem. Hence, the implementation will be put to use in a variety of industries, particularly the medical ones. Recent years have seen increased interest in brain age estimation, which will be extremely beneficial in the early detection of several neurodegenerative disorders. Hence, with neuroimaging data, deep learning has a great potential for precise disease prediction. However, the performance of the prediction is frequently constrained by the size of the training data set and the memory requirement for the computer. So, reusing a previously trained model in a different problem is known as transfer learning. The ability to train deep neural network with fairly little data, it is now very well liked in deep learning, since the majority of real-world situations often do not have millions of level data points to train such complicated models. That is particularly helpful in the data science field. Therefore, in transfer learning, a machine uses the understanding it has obtained from one activity to enhance the understanding about another. Although the transfer learning provides a number of advantages, its key benefits include reducing the training time, improving the neural network performance in most circumstances, and using less data. Motivated by this research would adopt the transfer learning approach. We've conducted several reviews from 2016 to 2021. We've seen numerous number of algorithms that have been proposed in the literature, which include the conventional machine learning, the extreme learning, the CNN, the LSTM, the attention-based residual network, and other approaches. However, a study was conducted in 2019 by Ashfar, who uses extreme learning machine on open neural data set. The results were relatively okay. However, the amount of computation time that was needed to look was too high. There is no doubt that the computational time of the extreme learning machine, the regression accuracy and data classification were also less. First, how to balance the performance and the processing time is an open issue, especially for application in high-dimensional data set. For this reason, among others, a different method for extracting more features need to be explored. And this has motivated us to explore more approach. Hence, for this study, we use a 2D axial mid-slice picture from the brain MRI scan volumes and demonstrate how this image is divided into 3 categories based on the participant chronicle age. In our approach, the 2D CNN is a future of 2D slices and is easily parallelizable. This feature presentation are then fed into the network to capture the global age information to further enhance the effectiveness of the feature engineering. We apply analysis to reduce the dimensionality while the features are extracted at the convolution layer. The obtained MRI dataset was utilized to adjust and train the pre-trained rest in the shell method, which we presented in the next figure. This is the proposed framework for the system. We built the image feature space using the pre-trained ResNet models using off-shell CNN features, where training is only done on the final application layer. However, as a result of the image high dimensionality, we use the PSA to project the high dimension feature space into a lower dimensional related features we are discarded. Such crucial class decomposition to create more homogeneous classes and lessen the need for memory and increase the framework's effectiveness. Hence, the total amount of data is divided into training and testing set, as can be witnessed. We've seen that the training constituted of 70%, and then the testing was 15%, validation 15%. Conduct the experiment on MATLAB 2021 on Windows 10, 64-bit operating system, and 8 GB RAM. Hence, the study trained 3D anatomical MRI images of the brain from 620 study participant ranging in age, which are part of the open neural data set. This data set is used to implement the proposed model. The 3D brain volumes are available as zip file in the Neuroimaging Informatic Technology Initiative format. The participant ages ranges from 3 to 34 years. Participants are divided into 3 groups. That's 3 to 5 are children, 7 to 12 were also children, and then more than 18 were adults. We set the testing and validation data to have 15% each, while the training data has 70%, as stated earlier in the framework. These data set divisions are consistent throughout the 3 ages group, including the 2x offline data accumulation carried out. There were 1,240 images in total from 620 individuals. This separation results in the following image size shown in the figure. This figure demonstrates how we split the data into the training, the validation, and the testing state for each class of each. After the simulation, these are the results that were recorded. We use the sigmoid activation function, and then we vary the number of epochs to determine the performance and the optimal value. From this table, we can see that the epoch, as the number of epoch increases, we are witnessing more decrease in the RMSE, which means a better prediction performance. For this case, we have seen that the model gave a base RMSE at 20 epoch. We also varies the number of the hidden neurons, and then we simulate. From this table, it also shows that the number of neurons have significant impact on the prediction accuracy of the model. Clearly, we can see that as the number of hidden neurons were increased, we are witnessing more reduction in the RMSE of the model. RMSE at 300 neurons. We then move further to the same data set using another approach proposed by machine. We've seen that comparing the proposed system and the existing extreme learning machine approach, we've seen that there is significant improvement in terms of accuracy by the proposed transfer learning approach compared to the extreme learning machine. Clearly, we can see that at the neurons 800, we've witnessed the proposed model having the best RMSE of 1.0981% compared to the extreme learning machine, which have 16.8%. Also, we try to look at other studies that apply the same data set using this similar deep learning approach, such as the 3D ResNet 18, the 2D ResNet 18 plus LSTM, and the SFCN, convolutional neural network. We use a different metric in this case, which is the mean absolute error, the MAE, to determine the prediction accuracy. Clearly, we've seen that the proposed model attained 0.81% accuracy in terms of MAE. When you are comparing this result to the extreme learning machine, in terms of MAE, we can see that the extreme learning machine have shown a superior performance than the transfer learning, which is one of the major limitations of the work, and we hope to address and see how we can improve the proposed model performance accuracy in terms of the MAE, the mean absolute error. In conclusion, the research uses the model that has been trained for one job as a starting point to train a model for a different task. It's frequent deep learning methodology that is used to classify a new set of images. And transfer learning typically speeds up and makes it simpler to fine-tune a network more than training it from beginning. So experimented on 2021 MATLAB version shows that the model attains the best case for 20 epochs. Also, we've seen that the number of neurons has significant impact on the performance of the proposed model. And then on comparison with other baseline model, we've seen that the ResNet 18 have a better MAE than the proposed model. Hence, in our future work, we hope to address the significant gap that exists between the extreme learning machine and the model for the MAE. And then also, we would like to use other evaluation metrics such as the MAPE, precision, and then the processing time to evaluate the quality, to be an index for evaluating the quality of each of the models. These are the references. Thanks for your attention.
Okay, Mustafa, thank you very much. Dear colleagues, do you have some questions to Mustafa? Maybe online? Okay, I have one at least. Have you compared the accuracy of the network versus accuracy of a doctor? I mean, is it hard to classify the age of a brain?
Okay. Actually, but when we are dealing with why we're bringing artificial intelligence to solve this issue is when you have plenty data that become impracticable to predict. That is when AI will play an important role and can give you a very good prediction within a shortest time.
Okay, thank you very much, and good luck with your work. Bye.
Thank you very much. Thank you.
Okay, and the next presenter is Israel Huaman, offline at least. We're very glad to listen to someone offline and online too, of course.
Okay, good afternoon, everyone. Today I'm going to talk about our research project here that is named Coupling 1D blood circulation model and substance absorption model to study drug metabolization. So we'll start with a little introduction about our goals and our challenges that we faced. So our first goal was analyze the entire process of drug administration. That starts with an initial insertion of drug, of course. In this case, we took the case of intravenous insertion, which develops in a sub-process like absorption, distribution, metabolization, excretion. Another goal was to make this model simple as possible, like computational friendly, let's say, because if you want to express some circulatory models, you can go as complex as you wish. So it was important for us to make it quite easy. So we move forward with 1D model representation. Okay, so some problems we may face was the drug properties, because there's a lot of different types of drugs with different characteristics. Not all drugs have all the same aims. Some drugs have different targets. Well, also some vessel properties that may vary. I don't know, diameter, longitude, tissues is not the same a healthy tissue as a tumor tissue. Well, body position, even just bending the knee influences on the blood propagation through the body. Another, well, as I mentioned, this the demanding computational task. I said again, it's a very detailed model could be really difficult to portray, to simulate. So yes, we selected a 1D blood flow model. Okay, once we have defined our 1D model, we go forward with some of our methodology. We start with an agent insertion that happens after some stabilization time that should pass. I will go if I have time for that. Well, the agent propagation that happens, that occurs thanks for our hemodynamics established previously in our 1D model. And well, the drug absorption and excretion that will represent the decay of drug presence inside our system. And well, to make it more realistic, of course, we need some agent reinsertion to represent all the flows that in real life happens, because the blood should transit all the body. So a little bit more deeper on the 1D model. On the left, we can see a good representation of different arteries on the human body. Each artery has specific parameters that we take into account. And on the right, we see well, a little bit of dynamics taken from Sviatnikov system that describes, for example, the well, the area of some vessels and the velocity of the blood flow, which well, we see on a nice animation in the middle, which is the blood sorry, the circulatory system with some fancy colors for representing the correct blood propagation. Okay, once we have our 1D model, now the second stage will be our absorption rate model. For absorption models, we have different kinds of representations possible. In this case, we started with one compartment model, which assumes that the whole body is just one kind, well, is treated as just one kind of tissue with similar properties, let's say. And well, after all the drug is treated, well, metabolism process inside the body is at the end excreted, is eliminated. Well, I think the equation is quite explicit. We have an initial amount of drug inside the system in the main compartment, and well, through the time there is one elimination constant that is expressed by this k here. Yep. And then, well, it should be increasing across the time. So that's the second part. Just a brief showing that, okay, in our case, we're taking a single compartment model, but could be, for example, two compartment models that at least make some differentiation between, well, a central compartment will be organs that are directly involved on absorption processes. And well, peripheral compartments could be like, I don't know, second tier in importance parts of the human body. Or we can go even more detailed with assigning one compartment to each kind of tissue of the human body. Let's say, I don't know, bones or muscles with different porosity or different properties. So once we have our 1D model and our absorption model, we have to put them together, do some coupling. So we have a T0, which is assumed to be after one stabilization process is done. So we can see here that the drug starts enter to the system at the time 0.5, and it starts to propagate across the system until it starts to leave. So we see at the end less amount of drug in the systems that will re-enter, again, reduced in a reduced amount. Well, some brief results. We can graphically see the drug concentration decreasing. In this case, we test a drug named epinephrine that is quite used and is popular because it has a very fast absorption rate. Here we see an example on 10 minutes, I guess, yes. And we see how the drug is almost totally removed from our system. Then as a second result, we see how the drug concentration decreases, but in this case with ibuprofen, that is, well, another popular drug. In this case, we run it almost a half hour, and we see how the decreasing happens. But again, not totally. To have a total elimination, we should run it for a couple of hours, maybe days. So this is a more nice animation to show graphically what happens. Here we see the first 10 seconds, that is the stabilization time I mentioned before. And that suddenly peak that we see at the beginning is the insertion moment. So of course, it's all the amount of drug inserted, so of course it's kind of big. Then we see like the reinsertion process happening. Once the drug leaves the system, should re-enter, but in a decreasing amount of drug. So this is what happens in a left coronary artery topology. So we have a bigger one. For these animated samples, and because, well, the time is short, we selected a very high elimination rate for this artificial drug, let's say. So in this case, we see a very, very big elimination rate that happens almost instantly by the second 20, and a very high detailed topology, which takes 50 arteries. We see again the stabilization time, then the increasing of the drug, and then almost an immediately elimination. And we see just a little bit of traces of drug in the arteries of the bottom. So, well, as future works, we would like to do a wider verification of the implemented one compartment model with long-term dynamics. As I previously showed, our longest dynamic was like a half hour, which, okay, is good, but maybe not too realistic to portray a full absorption, which will take hours, maybe days. Then find an ideal, or implement, why not, multi-compartment model absorption, because right now we are dealing with just one compartment model. We would like to give, I don't know, maybe more detail to different kind of labels. So we're good. Then, well, the application of our most detailed model to a general drug to a well-known rock, because right now we're testing like with very fast absorption rocks. Well, that's all. Thanks so much for your attention, and I'm ready to answer some questions you may have.
Thanks, Israel. Dear colleagues, do you have any questions?
Yeah, nice presentation. I love the animations. How do you validate the model? Like, what's the
Sorry?
How do you validate the model? Like, what's the ground truth? How
Mhm.
do you know it's
Oh, well,
correct?
for example, for the case of epinephrine, we know that it's a rock with fast absorption rate, which is here. So, well, the how to say it, the average time of half-life, that it means that is half of the rock is absorbed, is like 3-5 minutes, which is quite realistic in this case. We see a 10 minutes simulation, which shows that the amount of rock is almost totally absorbed, which is correct in this case for the epinephrine. Same happens with the ibuprofen. If I'm not mistaken, the total time of absorption of the ibuprofen may be a couple of hours or even days. So again, we saw in a period of half hour, we see a big amount of rock absorbed, eliminated, but it's not all. So the results fits inside the how to say it, the expected realistic results that are well known. So that's it.
Thank you.
Sure.
Dear colleagues, do you have any other questions? Maybe we have some questions online. Okay, I have several, if you don't mind. First of all, I would like to continue the previous question. It's really interesting if you have some method to check the results experimentally. I don't know how, but probably have some plans to verify these results. Somehow, do you have some plans?
Oh. Well, I think the first measure was that, like comparing to most to what we have on well, how to say it, on literature, what is well known. But yeah, maybe I don't know. Future plans, we can think on a better methodology to test those results.
Yeah, because this problem of fluid flow in vessels is really complicated, and you use a bit simplified model, so it's really interesting to estimate it. Okay, slide. Oh, by the way, we have this slide right now. We have this upper plot drug concentration, but you have a lot of vessels. What does it mean? Just one number, drug concentration.
I think I didn't mention, but the results are tested on a very simple model. But I think it's stated here. I don't portray it, but it's a really simple model that it has just one inlet node and 2 outlet nodes. So when the rock leaves, it just combines and then returns to the initial node. So it's like a very simple topology. I don't know if okay.
Yeah, okay, I get it. And slide number 5. We can see these beautiful equations from mechanics of continuum.
Here I guess. Yeah.
Number 5, the right side of the slide.
Yeah.
Can you explain the physical meaning and the boundary conditions that you use solving those equations?
I think maybe my co-authors can give me a better lecture on those equations. I don't know. You can help me, Oleg or Paul. Yeah. Maybe.
Describes the relation between the local area changes of the vessels and the velocity in these vessels and the forces acting on this well, on the blood locally. So the boundary conditions that we use here are a preset pulse wave. So it's the heart is represented as a pump that gets a specific pulse wave for each heartbeat.
Yeah, okay, I get it. Thank you very much. This is very interesting work. Wish you luck with this work, with the research. Thank you. Okay, we have the next presenter is Nikita Ditkov in the online mode. So Nikita, please share your screen.
off and I can't hear. Do you see it or not?
We can hear you. Everything is fine. You may start.
So, yeah, hello, dear colleagues. My name is Nikita Jitkov, and I will present you our work called Exploring the Relationship Between Error and Interpretation of the Segmentation Model's Prediction. So the problem of neural networks as black boxes is already well known. We almost can get the reasons of the deep neural network making this or that decision. And when it comes to the domain where people occur, especially in the medicine domain, it becomes clear that such methods need to be implemented in this area. For example, if you want to help doctors with the system detecting cancer, we have to ensure that we have to ensure the doctor that the system is making predictions based on something that the doctor itself can understand. So our initial goal is to study the segmentation interpretation methods and apply it to the medical data. And after that, we dive deeper into the analysis of those methods. So as data, we have chosen the dataset of microscope images of the kidney. There were big images in TIFF format, and the task is to detect segment functional tissue units on those images. Here you can see the example of the whole image and the zoom in with the functional tissue unit. So first of all, we made a dataset of crops and trained LF models. Then after that, we have chosen the best one and continued with it. Here you can see the examples of the predictions. And first of all, there is crops, there's true masks and predicted masks. And in general, it works quite well for different types of objects, but there is one issue with one of the samples here. So here you can see that in the ground truth mask, there is just one object in the corner here, while in the prediction, there are two of them in the corner here and another one here. So in the prediction, this object has a correct form of shape of the FTU, functional tissue unit, but there is no such an object in the labeling. This object is the false positive object. But why is it here? We need to interpret this. So our model is a deep neural network. It's a so-called black box, and we need to know because of what features it outputs such prediction. In a nutshell, the idea of interpretation is quite simple. We just reverse the activations of interesting neurons and obtain an interpretation map showing which pixels gave the most information. In terms of segmentation task, we use layer level interpretation algorithms such as layer activation, layer gradcam, and layer gradient shed. Because of the fact that our deep neural network has a lot of layers in decoder, our model is UNet. We choose to use all of the decoder layers and fuse its interpretations, since we can get more spatial information from those. So here you can see the examples of application of those interpretation algorithms to randomly selected layers. So here we have the crop here and its interpretations. So here we can see the collage of the input image, its mask, prediction, and three interpretations. Those interpretations differ from each other, but in the true mask, there are two objects. Those objects occur in prediction and in all of the interpretations. But also there is another object that's showing in the prediction, slightly showing on the leftmost and the center interpretations, and is showing and can be clearly seen on the rightmost interpretation. So we shall treat it as a false positive object also. But here's the thing, on 2 of 3 of those interpretations, this object is very dim, so it hardly can be seen, actually. Hardly can be identified. And here is our idea. So if we see a disagreement between prediction and interpretations, we can use it as a filtering rule, removing possible objects from predictions as the post-processing step. Thus, we shall be able to remove false positive or false negative errors from the predictions. To verify it, we collected the images to test this hypothesis, processed them with the model, manually looked through all of the predictions, and selected ones that have false positive or false negative errors, and then we obtained interpretations of those images. So we have 14 images with false negative and 26 with false positive. So here is the result of our analysis. We looked at each interpretation and prediction and counted number of times when error object from prediction also shows up in the interpretation. And unfortunately, there are just several cases when there is no false positive object in the interpretation, or there is false negative object in the interpretation. Also, we analyzed whether there are, so it's about the table number 1. Also, we analyzed whether there are other objects on the interpretations that can be identified, but they are not false negative or false positive errors objects. And the results are in the table number 2. After all this, we can say that the reliability of the interpretations in our exact case is not sufficient enough, and our K hypothesis is not correct, unfortunately. But we have another one. So here is it's a strange thing that model can be so confident in the object, and if the interpretations are also so confident, maybe it's not the model's error actually, but the human's error. So our hypothesis is that using agreement of the prediction with interpretations on some object, which seems to be an error, we can make assumption that this exact data sample is just wrongly labeled and need to be reviewed in the dataset. So yeah, here it is. We developed a method for analyze the relationship between error interpretation of the segmentation model's prediction. We applied those methods to the medical images. We analyzed the co-occurrence of false negative and false positive errors in prediction and interpretations, and proposed a method of searching of the errors in segmentation and medical datasets. So our future work and direction of movement is in replacing an expert looking for the information about error because we manually checked those by some algorithm. Thanks for your attention.
Thank you, Nikita. Dear colleagues, do you have any questions? Any questions online? Nikita, I have terrible question. Would you please explain the main hypothesis again? I mean, the topic of this research is really interesting. And would you please briefly again the basic idea that works?
So we have some image and this true segmentation mask. Also, we have a prediction of our model, and we can see that there is some error object. So in this case, it's false positive object because we have it in prediction, but we do not have it in the true mask. And we can get interpretations, those interpretations from this prediction. And our hypothesis is that if there is no such an object in interpretations, for example, here and here, we can see that this object is very dim because it's quite a red object here and just a slightly white here, and there is a strong border, black border here, and almost no border here. So we can think of it as of the this object is not actually very presented in those interpretations, but in this interpretation here, this object is clearly seen. So our hypothesis is that if we have disagreement between interpretation and prediction, we can use it as a filtering rule for those kind of objects that seem to be false positive or false negatives. So as an expert, myself, for example, I looked manually through all of these examples where we have false negative or false positive objects. I looked through their interpretations and I tried to find a rule whether there is such interpretation or such I don't know, some rule where we can say that interpretations are in disagreement with the prediction, and we can and looking at these interpretations, that doesn't have such an object, we can filter out this object, again one here, from the prediction, getting the right number of objects. And we have manually checked all the objects from the test dataset that has such an objects, false positive and false negatives. And unfortunately, we haven't. So there were just several objects, several cases where we can filter out those objects. In the 90% of times we couldn't do this. It's about all of the interpretation methods, and the key hypothesis was this one.
Okay, I didn't get it anyway. What is the filtering rule? But I hope I read this paper in more detail. Probably will continue the discussion. And also one more question: what is this sum column? Yes, no, and sum. Is this a kind of class or what?
It's the column saying that there is not some object that cannot be identified as the FTU, as this object, like round object, but there is something. So it's not just a blank space, but there is some irregular object that cannot be identified as functional tissue unit that we are looking for. But anyways, there is something, and this column is saying about this.
Yeah, okay, I get it. I read the paper. I can send it to you if you like, with the trick when the network can have some doubts. It can predict yes, no, and I don't know, something like that. And this trick may works sometimes. Okay, Nikita, thank you very much.
Thank you.
And the next presenter is Alexandra Matveyeva. Her presentation will be online. Alexandra, you may share your screen.
Okay, just a second. So, is everything all right?
Yes, we can hear you. We can see your screen. Everything is fine.
So, good afternoon, dear colleagues. I'm Alexandra, and now I want to present to you our research work, application of Gaussian process regression as a surrogate modeling method to assess the dynamics of COVID-19 propagation. So, mathematical modeling proved itself as a useful tool to characterize the dynamics of the spread of diseases such as influenza and COVID-19. Outbreaks of coronavirus infection have had a significant impact not only on the global economy, but also on the daily life of each person. In this regard, there is a need for tools capable of modeling the spread of infectious diseases. So on this slide, you can see the main topics that will be discussed today. We will talk about a little agent-based modeling, surrogate modeling, and Gaussian process regression, and etc. So let's start. There are many types of models for predicting and explaining the dynamics of the epidemic, including compartmental and multi-agent models. For a more detailed description of the processes of virus spread, an approach, so-called multi-agent modeling, was created. The basic principle of multi-agent simulation is as follows. Each agent in the population interacts with other agents if they attend the same school, workplace, or live in the same household. And in this table, you can see the main input parameters of the model, the fraction of non-immune individuals in general population, infection transmission coefficient, and initial number of infected individuals. Of course, agent-based models have some limitations, in particular, high-level complexity of parameters, long execution time, and complexity of model analysis. So due to the presence of stochastic processes for model calibration, as well as the need for uncertainty and sensitivity simulations, with sensitivity analysis, it is necessary to conduct many simulations, which leads to increased time consumption. And on this figure, you can see the example that the simulation time increases with the increase in the main parameter of the model. And to solve the problem of time-consuming calculations, we can use surrogate modeling. The main idea of this method is shown on this slide and consists in the following. The original model, or part of it, is replaced by a surrogate and is presented as a black box in which the main problem is to find the dependence between output data and input parameters. There are several methods of surrogate modeling, and the problem of this research we can solve using data fit methods, especially Gaussian process regression. Gaussian process regression is a class of supervised machine learning algorithms for which it is sufficient to use a small number of parameters to make a prediction. And covariance functions are an important component of Gaussian process regression models. And the following kernels were considered in the research: rational quadratic kernel, radial basis function kernel, and additive kernel, the combination of rational quadratic and radial basis function kernels. So to train the model, it is necessary to form a dataset by repeatedly running the original agent-based model of COVID-19 propagation. To perform this, the synthetic population of St. Petersburg was used. There are about 2 million agents in this population, and modeling on such a large set takes a significant amount of time. And in this case, there is a need to conduct research. With a sampled population, and to perform this, sampling algorithm was used. You can see it on this slide. After sampling, the population was reduced by 4 times, from 2 million agents to 500,000. On this figure, you can see that with a sampled population, modeling is much faster. So what about our results? From on this slide, it can be seen that the model does not work correctly with radial basis function kernel. At the same time, surrogate models with rational quadratic kernel and additive kernel allows to track the approximate dynamics of propagation with all input parameters. And it is also clear that Gaussian process regression is trying to smooth the dynamics. And to improve the results, we tried to smooth the initial data and got the following. How we can see from this figure, radial basis function consistently gives an incorrect results on these parameters. So based on this, we can conclude that this kernel is not a priority for use in Gaussian process regression. And our kernels give us the better results compared to previous simulations on not smooth data. Metrics also prove obtained results, and these tables show that for a model with radial quadratic and additive kernels, the values of the coefficient of determination increased by 0.14, and the mean absolute error decreased by 5.31 on average. And the obtained results demonstrate the possibility of estimating the dynamics of the COVID-19 propagation at different values of input parameters by using methods of surrogate modeling. And a little about our future plans. In future research, it is planned to replace the expensive calculations of the multi-agent models with a surrogate to assess the full dynamics of the COVID-19 propagation. Full dynamics, it is near 80 to 100 days. And to perform uncertainty quantification of multi-agent models using this Gaussian process regression. And in the little conclusion, in this research, a surrogate model was implemented to replace time-consuming calculations of multi-agent models, and 3 types of kernels of the Gaussian process regression were considered. The best results were shown by the rational quadratic kernel and the additive kernel. So that's all. Thank you for your attention. I'm ready to answer your questions if there are any.
Thank you, Alexandra. Dear colleagues, do you have any questions? Yes, sure.
So nice presentation. So you told you used the Gaussian process regression. So why haven't considered the sparse Gaussian regression? Because I'm also doing something similar regarding the sparse Gaussian regression, because the complexity of Gaussian regression is dependent on the number of training point in the data sets, right? As you told, you did some sampling and reduced to quarter half million. But if you use the sparse Gaussian, it has the way of reducing this with sampling by inducing points. I think it will give you high accurate result.
Oh, it's very interesting. It's very interesting. So, could you please repeat the question?
So how would you reduce the dimension? I mean, what's the criteria you use to sampling the data reduction from the original data set?
You talk about sampling of, yes? No?
Yes, yes.
Yeah.
We choose the we just choose the number to reduce the initial population to perform simulations on initial agent-based model more quickly to form the data set.
Okay, thank you. The next question.
Thank you for a very nice presentation. You mentioned that your plans are to apply the surrogate for uncertainty quantification and also for full-length, full-scale dynamics of the pandemics. So can you estimate how much data you will need to train the surrogate? I guess you will have to run the model for the entirety of this time, at least a few dozen times, to get a good training data set. Or maybe I'm wrong.
In this part of research, we just try to understand, is it possible to use Gaussian process regression? And I think that in the future research we will think about this, how much data we need for this, and I think that's all.
Okay, one more question. Have you thought about trying to cross-grain your model with the surrogates? So maybe to use a single surrogate for several dozens of your initial agents?
So in this research, we try to replace the whole model, not the small part of the initial agent-based model, but the whole, if I understood the question right.
All right, thank you.
We tried to use surrogates for those households. Actually, we thought that maybe a single household could be made of a surrogate. But there is a lot of nonlinearity there inside, so we were trying to untangle it, but still we're struggling with it. It's kind of complicated. So maybe we will manage to do that in the near future, but at the moment it's not entirely clear how to do that.
Okay, any other questions? Maybe online? Okay, Alexandra, do you have prognosis for us about COVID-19 for the next few months?
Not yet, sorry.
Yeah, okay. Okay, then good luck with your research. Dear colleagues, we have 3 more presentations. The next presentation by Sergei Stasenko online, and then 2 more presentations offline. Sergei, you may share your screen and start. We can see your screen, but we can't hear you. Sergey, your microphone is turned off.
Good day. My work is related to the field of computational neuroscience. You can see, you can hear me.
Yes, everything.
We present a mathematical model of astrocytic regulation of non-periodic bursting activity of spiking neural network. It's very known that bursting activity underlines both normal physiological processes like cognitive function, arithmogenesis, and pathological ones like epilepsy. The model considers a spiking neural network with a layer of glial cells, astrocyte. So you can see it on the right figure. This is figure of neural glial network, which experimentals take from the microscope. And the astrocyte can regulate excitation and inhibition and the neural network. Astrocytes do their processes included in signal transmission circuit between neurons and regulate neural activity and synaptic transmission in kaizen-dependent way. After generated spikes on the presynaptic neuron, some of the neurotransmitter can diffuse into extrasynaptic space, so like this, and bind to the receptors on the astrocytes at here. And this is turned to some biochemical reaction, resulting in the release of glia transmitter, which can regulate the presynaptic and postsynaptic terminals. On the next slide, you can see the scheme of our model. At here, we take 20% of inhibitory neurons and 80% of excitatory neurons. And in the right scheme, you can see the scheme of tripartite synapses, which include presynaptic, postsynaptic terminals and astrocytes, and some interplays between them. For modeling of neurons, we used Izhikevich neuron model. So you can see it here. This is some kind of system of different equation. And in the right part of this equation, we add I noise. I is the synaptic currents between neurons, and I noise, this is eventually distributed noises. And for modeling dynamics of neurotransmitters, and we add to the model average neuron activity, which feed of spikes at neurons, and can in simple way to transform it to the some filters. And this is Q. This add to the equation for neurotransmitter concentration is the right. And when the neurotransmitter released from presynaptic terminals, it result in some activation of astrocytes and release of glia transmitter, which dynamics is described by this equation. And after some glia transmitter is high concentration, the astrocyte can influences on the weights of neurons this way. And we can see it in three cases. In one cases, when we have no astrocytes and we have no some noise, and in these cases, the model is in excitable mode. So you can see this slide, and no way this bursting activity here, but always is change when we add some noises to the neuron, and non-periodic bursting activity is presented here. But when astrocyte is active in tripartite synapses, they can off this bursting activity by acting to the synaptic transmission, depressing there. So this is the main results of our model. Thank you. Any question?
Thank you, Sergey. Dear colleagues, do you have any questions? Maybe online? Sergey, would you please share us the ways for practical use of the results of your research?
Practical use of our research is connect with the experimental work, because in some way, I don't add to this presentation, but in some way, when experiments, neurobiology, they take some data and they see some effects, they cannot understand in simple way what influences on this complex system is present. And for example, this mathematical model can explain many different roles of astrocytes in complex dynamics.
Okay, I see. We have really powerful lab in Oriol, Laboratory of Biomedical Photonics. I think that their research is really close to your work, so please welcome to Oriol. Okay, Sergey, thank you very much. We are going to continue.
Thank
the
you.
next presentation is by Levon Abramyan, offline presentation, and the final presentation by Gisara Kulatunga, also offline.
The topic of my research, not only mine, it's predictive dynamical interpretable modeling of disease trajectories post-operative observation after myocardial infarction. Heart problem is the most common problem and most common causes of death in modern, and it's a reason to research that. For our research, we have some data provided by Almazov National Medical Research Center. The data includes some electronic medical records from 2012 to 2021, and we use some NLP methods together with doctors and found it about 300 patients with operation after myocardial infarction, and we now label about death, diabetes, second infection, and heart failure. Our goal is build a model that describes the dynamic of change in patient's condition during recovery period in hospital after surgery, and trying to build some graphs with states and get some information during the 5 years. In this topic, we will speak about def label in this research. This is research plan. Begin of it is start is very classical. We receive data, use some standards method to make feature engineering and model engineering, and after that we did some dynamical interpretable modeling. First idea, it's classic idea. We want to interpret our models, and for that we have to reduce the dimension. Advantages with removal of multicollinearity. It's important if we want to use some linear model, avoiding the curse of dimensionally. Medical data have some feature. We have a lot of columns and our dimension is large, and curse of dimensionally it's maybe becomes a problem. Reducing another advantage is reducing the influence of noise and getting new feature and trying to use with old. But except that, our idea and use states in different time periods. What we have did, dividing the features in time intervals. For example, it's operation date, first day after operation. It was day we have some blood analysis. First week we have some we have EKG, and in this research we have a label about death in 5 years, and we getting some graph using edge only between these vertex, and after and into every new columns we need to use some clustering, because operation date has a lot of columns. We have to get one new feature, and for that we need do some clustering. Its example, we can do more labels or less. It's just a schema. For example, what we have some results. We can, on the left side, original label, and in right, what we got. We first class and second clusters describes the def label on the left. It's we can see in that graph, and difference between that it's significantly different. It's important thing how we get that rules, because we have some patients, some analysis and use clustering. But for that we use Schult overfitting tree decision tree. Overfit need to get some rules. If we use overfitting tree, you have much complicable rule, but and your percent will be more. Its number show how many peoples with that rules is cluster 1, for example. If you use not overfitting tree, rules becomes easier, but Q% is getting low. And it's just an idea. We have we use it overfitting tree because we want to get rule for our clusters. And after that, we build some Markov chain and some graph. We can see in this chain problems because we have a lot of patient with labeled 0 in 4 and 5 days. For 5 days, it's features for diabetes, and it's not good. For solve this problem, we build another model. Before that, we build some machine learning model using XGBoost. We can see result using with scaffolds. But as I said before, at this moment our model is not good. For improve that, we did some future engineering using SHAP with previous model, but we did not use H because H is invariant. We want to use some dynamical future that can be changed for into time intervals. And we did not use alpha-theoretics because it's one math label and we have only one target. It's not good. Only one feature, and it's why we did not use that feature. And we rebuilt our models. We have good results with, for example, 1 week. We can see on the left its original label. Label 1, it's def label, and on the right we can see cluster 2. It's like cluster 1 into cluster 1 in the left. And is this rule? It's not hard to predict that. For cluster 2 is original label def1. After that, we rebuilt our graph, and now it's we avoid that problem and previous chain, and we can see what if patient have label 2 after 1 week. It's a bad target for him because very many patients after that in 5 years getting label 1. After that, we use some machine learning. On previous use XGBoost for that. In previous, we have with new data scores 0.7. Now we have 0.8. It's mean our reduce of columns. It was a good idea, and we have to do some future works. For example, we can use different clustering models. For in begin, use the model for other disease like second heart attack or diabetes, and maybe made some automatic. And after adding some patient, every time graph will be changed. thanks for attention. If you have questions,
Okay, thank you, Levon.
I will
Dear colleagues,
answer it.
any questions?
Thank you for your presentation. Very interesting. I have a bit more, I guess, philosophical question. What have you learned from your model? And if you go to a clinician, for example, and talk to them, how would you tell this clinician to reduce deaths, for example, based on what you learned from your model? Can you do something like that?
Can you repeat, please?
So you have found all these paths
Uh-huh.
for patients
Mhm.
and the correlations that
Mhm.
eventually lead to the patient's death 5 years from the.
Mhm.
How can you interpret these results? And
Mhm.
how can you, for example, advise a clinician what they should do to reduce this amount of deaths, for example?
We can use wet graph to predict probability of some disease in start of disease. For example, we have a patient with operation of after some heart attack, and we want to know what he becomes a how would say a problem patient in start is his disease. It's to do it clean. It's we need to do some many steps. Like for that, what we now, for example, in our data, for example, death 5 years, it's about 80% died from heart problem, but also we have patients who died in different reasons. It's not good. It's also a point where we should become better, and our model should become better. And it's a start of idea, and I think we will do it.
Okay, thank you.
Any other questions? I have several, if you don't mind.
Don't
Well,
mind.
first of all, this research is really important, of course. Would you please explain in more detail the content of the experimental data? I saw that you have blood count test results. Would you please remind how many patients you have in the data set? How many input features? Well, it's clear what output features.
Total patient about 3,000 patient with this label, but in VDEF we have less because it's difficult to for that we have natural reason, because if patient becomes in Almazov National Medical Research Centers, and after that just move to another city and another country, we don't have any information about them after 5 years. In 5 years, and we can get label 0 for him because we want to clean data. For death we have about 300 or 400 patients.
And what about the number of input features?
Input
Blood count
features
test results, it's about 20 features, right?
Total was about 40 features, but after some working with categorical feature, it becomes more.
More, not less.
Not less. In start, what of course, if you have categorical with 4 different value, we used if 4 new columns with 0 and 1.
All right. And one more question. Have you ever thought about the way to check your model you may try to solve simple classification problem or fitting problem. For example, you will try to predict lifetime of a patient. This is supervised learning. Have you compared your model with such a simple supervised model?
And with a supervised model, at this moment we don't not compare it. And as I said, it's just for this moment we do some models, but it's just an idea to improve this work.
Yeah,
Because
that's a good idea. Yeah, right. Okay, I see. I think that the data set that you have is not really large, right? You need more data.
When we started, we works with diabetes. It was our main goal, but we have medical data have some typical problem. We have any non-value, but it's not about our data in operation, first date, first week, and target, because operation it's we select people who was operated. If you was operated, of course you in first day you did some blood test, and in first week you did some EKG test, but in 4 or 5 day not we have made none values, and it's features for diabetes like LVNP, cholesterol, and so on. And it's also point when we have some solution for that, and the most important that on all of samples was watched by experts at doctors, and it's because it's important. Of course, I can see what if I see age 200, it's not good. I have some problem, but I am not expert to see some problems with the large value for medical columns, and they help us. And I understand for it's not more samples, but if we can reduce dimensions, we can use it, because it's typical problems too for medical research, because sometimes you don't have a lot of samples.
Yeah, I see. Very, very challenging problem. And one more question. Have you checked some international data sets? Because this problem is really frequent, some heart disease. Probably there is some data set on Kaggle or someone else. You may use it. Because one hospital is not enough, definitely.
Yes, it's we don't do it yet, but when we started the works, we together with that hospital and get from that with data and this moment.
Okay.
It's also a point when we can better.
Yeah. Okay. I
Become
see.
better.
Thank you very much. Good luck with your research.
Thanks.
And the final presentation today is by Gisara. Gisara, please. Gisara deals with control systems.
So,
Aren't you? Yeah.
good evening, everyone. So today's my topic is kind of off topic. I reduced set of slides to make it smooth and clear, and it won't take much time. So let's start. So the so the problem is that I've been doing the motion planning for the analytical way, like optimization and so on. So the idea is to try out the thing what I try to do with the deep learning base. So the objective is we have initial reference path which is shown in the orange color, and if that initially when it's given, we have no idea where the obstacle located and so on. So the when in real time when it flies, understand where the obstacles are located, and which is shown in the the pink color. And we need to refine the trajectory such that it's avoid the obstacle and get back to the original reference trajectory as close as it can. So that's it. So when we do the motion planning, we have the set of building blocks we need to consider. The one which is kind of crucial here, intermediate waypoint identifications, which mean if you consider this figure, so if your drone is here, which is in the red square, so when it get to the other point, initially it does the path planning in order to find the way it would be the optimal way to avoid the obstacle. So, but when this has to be done in real time, this is computationally expensive. So then the first thing we need to consider is the model. So usually when you consider the quadricopter, it's a 60 degree of freedom model which consists of 12 or 13 states, which is quite expensive to perform in real time like a small embedded computer. But what I would suggest to use the 4 degree of freedom model, which is quite easy to execute, which eventually does not give you more controllability, but eventually give you high computational power. The next thing is how you represent the obstacle. So in the simulated world, we all know the obstacle locations. We can estimate the Kalman filter, whatever estimation of the position of the vehicle, so the accuracy, everything is clear. But when it falls in real times, we have no idea about how the obstacle looks like. We have the less small range of the sensing range for the sensors which are attached to the drone. So it's a bit complicated. So then there are methods which are used for the previous works, the Euclidean distance transformation map, in order to find the free distance estimation. So that's the problem we're trying to solve. So let's assuming these are the obstacles which are unknown. So we need to refine a trajectory from A to B. So eventually we can solve analytically the reformulating the problem as a convex solve problem where the free space which is shown in the light blue color, then we can solve it. So the idea is I want to try the same thing from A to B. Let's assume from here to here, deep learning base. So what we have, we have the set of state. State is the current pose of the robot, and we need to generate the action. So the actions are the set of control command in order to maneuver the drone along the path which we want along this trajectory. So how we can do that. So then I was not much good at the deep learning. So when I start learning, checking, I try to use a two approach. First is the deep Q learning, and the second is the approximate policy gradient method. So the deep Q learning, so it's basically the Q learning. We have the table where we have the state and actions. Then we maximize the Q function in order to get the next optimal value. In the deep Q learning, just replacing what you have here with the deep neural network. As input, we give the current state to generate the set of action in order to move forward. The approximal policy gradient, it's a bit different because when you're talking about the deep Q learning, it's usually iterative iteration. Here, use the gradient iterations in order to learn the trajectory. So here we need compare to the policy gradient and the value iteration. So the policy is what we have for the value iteration, the gradient iteration. So the value iteration, what we have in the state. So then we have the next states and the next set of actions we told to move, and we generate the next state. So the two different complete ideas. So I'm trying to use both of them and check whether which one give me the better approximation. Just to compare in depth what has been doing there. So the DQN, we use the value iteration, and the PPO, we use the policy gradient. So the DDQ, can't do the online, but eventually when you apply the model in the real world, we need to have some online modeling. So which does the offline and generate the model and apply. Then it does not data reliability, not guaranteed, but here guaranteed since it's just directly optimized on the reward expected from the gradient. So then this is just a basic problem. In order to solve, we have the set of starting point and end points, and we generate set of environment in order to train the model. So then this is our state space of the model. So the case of here, we have the position and the velocity XYZ direction. And so then the action, what are the actions? So I decryptize the 3 degree of space into the 8 directions, where each direction is represented by the forward, backwards, upward, downwards, likewise. So the reward function is defined if the current pose and its need to get to the goal, and it's minimize the distance when it reaches the goal. So then this is the experiment result what I got from there. So what I did was initially there was approach, it was the published recently, so it uses the deterministic tree-based approach, which does not produce the real-time the accuracy. So what I did was I have my own differential model for the 3D, which I just explained, where I incorporate the uniform lookhate research. Deterministic tree-based, it's a Monte Carlo tree search. It does the optimal path based on what you have seen. But the uniform lookhate research, it's look for, if you consider the n-depth tree, it's look for all different type of path. Then we calculate the cost and get to the optimal path where it should move. But the computationally, the uniform lookhate search the deterministic tree search is faster, but when you're talking about the quadricopter and so on, we need to consider the safety. In that sense, we have to look through all the possibilities, otherwise we won't end up crashing the drone. So then we use the policy of proximal policy optimization with the different type of neural network in order to generate the control sequence. So this is what we observe. So in the analytical solution which we did last year, so we able to get 0.0 the execution time which able to perform in real world. But the case of any of these methods, see, maybe I'm not that good expert in these stuff. So what I observe is something around the mean execution time 2.2 seconds and 1.2, which the improved version. But in order to do the real-time performance, this has to be 0.02, 20 hertz or the 15 hertz per second. So this is what we observe at the moment. So the idea is to somehow to improve the method in order to generate the control sequence to move along the trajectory. So yeah, that's all what we did. So we trying to focus on more on improving the trajectory generation using the deep learning approaches. Yeah, thank you.
Thank you, Gisara. Dear colleagues, do you have any questions? This is the presentation from the other section, as you may see.
That's why I just skipped some bit more things.
Yeah, but anyway, reinforcement learning is the goal of some of the papers from our section too. So maybe I have some questions. Maybe some questions online. Okay, I have some. Would you please tell us a bit more about training environment? Is it computational experiments, right?
Yeah. So the training environment, what we have is something similar. So we use the OpenAI Gym for the learning. So then basically we generate set of random data points. Mm-hmm. So which is obstacle, and to get to the free space, we use the Euclidean distance transformation map from finding the free space from the current location to the obstacle, and we're trying to minimize this distance.
Oh yeah, I get it. And how does the reward function looks like?
It's just basically defining the distance, and this is the current location, and the goal location. It's trying to minimize the distance to the goal.
Just like that. And
yeah.
What about penalty condition? Is it? Do you have it?
No, any penalty conditions, because at the moment
interruption condition.
At the moment, since the execution time is higher, so if I incorporate more conditions, things not able to get any constraint, because at the moment no velocity constraint, or the velocity is the input for this, but we haven't put any constraint on the velocity as well. Because if you incorporate more, things get more harder and cannot get even what we observe.
Yeah, I get it. Well, reinforcement learning is really interesting and complicated problem. Of course, good luck, Gisara, with your work. Dear colleagues, thank you very much for your attention, for your presentations, and have a nice evening. Thank you and bye.